Assalamu alaikum warahmatullahi ta'ala wa barakatuh. Ladies and gentlemen, welcome back to another live stream. Please make sure to join my Discord server, the link in the description, so you can get to join us in DC while live streaming, and also to get notified about live streams, and also to be able to vote on next streams. So let me just share the stream. Live. Okay. Great. Yeah, I think we're good to go. I think we're ready to start. Stream seems to be fine. Mic seems to be fine. Okay, screen capture. Great. Great. Okay, let's start, I think. Let's start. Great. So last time we basically set up a lot of stuff regarding making a cross-platform application. We also have set up multi-window rendering, pretty much. We've also accounted for the resume and the pause event, the resume and the suspend event. So for like platforms like Android, like Mac OS, like what else, like Apple products in general. And yeah, we basically have this right now. We could actually create, no matter how much windows, each window gets its own renderer, but we're using they're using, of course, the same Vulkan device. And of course we also have the setup to actually create multiple Vulkan devices, which is actually pretty cool. Alright, so this is what we have left in the last live stream, or the first one. So today we're going to be starting some actual graphics. So we're going to be drawing, I guess, a triangle first, and then we're going to scale from there to a quad, then possibly a cube if we have enough time in this stream. So yeah. Alright, pretty cool. Love that. Alright, let's go. First of all, I don't really need 3 windows at this point. Just go with one. Yeah, you know, it's fine. Just go with no secondary windows for now. I don't need to test, but like when we want to test multiple windows, we could just increase that up and see about that. Anyways, let's go to our renderer. Lovely. So we basically need, like, currently we're not using any pipelines. Like, basically we're not using any shaders at all. I wanted to go step by step, and so by showing you how to use transfer commands first, which we actually used. So we used one command called clear color image command, which actually only needs transfer capability, doesn't need graphics queue basically. And yeah, right now we're actually gonna use graphics capability. So let's get started. Okay. Great. So let me grab Vulkano example so I could use it as a reference. Okay. So I'm gonna start first by not using buffers, not using Vulkan buffers. I'm just gonna be hard coding the vertices data in the shader itself, and then after we get a triangle, and then I'm gonna show you how you could use buffers. So I could go try to cover as much as possible, and you know, every time stepping up the complexity a little bit, instead of going all in, essentially. So let me make sure the live chat is visible. Hold on, pop out the chat. Let's go. Give me a second. Where's the example? There you go. Do this. Alright, now the chat is visible. Great. Okay, so let's get started, I think, by creating some shaders. I'm gonna actually go to the Vulkan tutorial and use that shaders, shader modules. Right, let's go. There you go. Okay, so let's see. So I'm gonna create an assets folder directory called assets, and we're gonna have shaders, a folder called shaders. Let's go. Alright, great. Now in this folder, we're gonna have a file. So it's gonna be let's see, shader .vert, right? And you could actually go ahead and install some GLSL extension, which I've already done. And now I'm just gonna copy this code. I'm gonna explain about this later on once we get a triangle, but for now this is what we got. Just two arrays in GLSL. I'm just hard coding the vertices data for now, and here we're just like making the GL position be the current vertex in, like, the current position with the index vertex index. So I'm gonna explain this more later on, but for now let's just try to get things working out, and then later on I'm gonna explain in detail what's up with that. So here we're gonna have shader.frag, and this is shader.frag. Okay, we're gonna get back to this later on. Anyways, so now we gotta create the shaders. All right, how we're going to do this, let's see. Right, now should we create shader for every single renderer? I don't think that's good. Yeah, we should probably try to reuse the same shader, so the same pipeline for all devices, hopefully. Well, depends on your use case, but yeah, that's what I'm gonna do, honestly. Yeah, fine. So we're gonna go to the Vulkan device, and let's go. So fn new. I think I'm gonna do it here for now, right? So let's, first of all, the first thing is, let's see. We're gonna be using, by the way, Vulkano shaders, great, which we have already added. So if you go to cargo toml, we have already added Vulkano shaders here. Okay, great. Now let's see what we got here. Well, actually, yeah, using Vulkano shaders, I'm not sure if we can use files. Interesting. Let me try. Let's see. So we're gonna be doing this. So mod vs, basically vertex shader, Vulkano shaders. Basically, Vulkano shaders gives us a macro that it would use to just compile the shader for us into SPIR-V, because Vulkan uses SPIR-V. And here we need to give it the source. Now I'm not sure if I could actually just give it the file. Let's see. Hold on. Not sure if you could do that with a macro. Hold on. There you go. Include str, and we could include shaders. Sorry, assets. /shaders /shader.vert. Not sure if this would work with the Vulkano shader macro, but we'll see. So include str instead of the string. I guess we could try this out. Expected string, no, it seems to be expecting a string literal. I see. Shader inner. Let me see if there's some other function that could take a file instead. Yeah, no, I don't think it can. Like, sorry, a string, but anyways, whatever. So I'm just gonna hard code this for now. I'm gonna just paste this in here actually. So let's go back to what we had before. Damn, come on, let's go. And I'm just gonna do this. And let's do that. Great. That's the vertex shader. Now the fragment shader. Mod fs Vulkano shader, and here it's say the type of the shader. Here in this case it's fragment, and in this case it's vertex. Of course, this basically happens in compile time, I think. I'm not entirely sure about how Vulkano does it, but yeah, let's go. And this is it. Now let me just copy my own shader here. Oops. There you go. Okay, great. Now, what we could do after this, we could say let vertex shader is equal to vs.load, I believe. vs.load. Let me see. Oh yeah, not dot, but it's a static function, right? So we're gonna load, we're gonna give it the device and the entry point. Okay, great. Let's give it the device. And we got a arc, like clone the arc, I believe, maybe. Yeah. But for now, I think it's fine. And then, well, yeah, we're gonna need to clone the arc actually. Let's go. Gotta give it a reference here, and the next thing would be is to just check if there's any error, and then we're gonna say entry point, and here we're gonna give it the entry point. In my case, I'm using the main function as my entry point in both shaders, so we're gonna go with that. Then I could just do this. Now I got my vertex shader, or should I say my vertex shader entry point. But anyway, let's fragment shader now. fs load, basically a very similar thing here. Device and errors, entry point, main. Now if you're using HLSL, you could use multiple entry points in the same shader module and use that basically. But I don't think Vulkano shaders actually allow HLSL. I think it only supports GLSL because in the background it's actually using shader C to compile the shaders for you. But yeah, other than that, GLSL only supports one entry point pretty much. So you can't do that with GLSL. There's also WGSL, which is very similar to Rust language, which is used by WGPU. You could probably try to compile that into SPIR-V and pass it to Vulkan too. But right now we're just using Vulkano shaders to make things simple. So yeah, the operator can only be used in results, not options in a method that returns. Okay, so these are actually options. So I'm just gonna unwrap these because I know for sure that wouldn't error, because I know that indeed the shaders does contain those entry points. So it's fine. Now now we got the shader modules, and in fact I'm gonna wrap this in its own kind of little what should I call it, scope, right? Because once I'm done with creating a pipeline, I could just destroy these shaders. They only have to live as long as well, basically once you create the pipeline, you don't need the shaders anymore basically. So yeah, anyway, unless of course if you're going to be reusing them in some other shaders, I guess, so that's something else. Anyways, let's go ahead and say here Let vertex input state. Alrighty, vertex. Okay, I'm not sure which one here, but let's go with the first one and see. Well, probably not what we want, but basically we gotta say per vertex actually. And then let's see if we can actually find the right import here. Shader stage is a variant, not a module. Variant. Weird. Hold on, let me check out the documentation of Vulkano. And let's check per vertex. It's inside vertex input. Okay. Okay. So let's import this one. Yeah, I think so. So like if you do right now per, come on, why it's not giving me, really? Oh, I think there's some other problem. Oh, I need to import some trait. Ah, I see. What is the trait? Okay, where's the trait in imported? That's stupid. What? Okay, let me go to per vertex. Which trait this is? Okay, let me try to run this. It's giving me, there you go. Okay, so let us add this into our code. Well, don't we already have this? Is defined multiple times, huh? Okay, what about this then? Okay, now I could say per vertex. Great, lovely. So that's what I needed. Okay, now let's go back to the example, and then you say dot definition, and then vs dot reference to vs dot info. What? Why it doesn't contain info? Interesting. Honestly, let me just copy this. Why not? And let's see what's up with this. Oh yeah, vertex shader, my bad. Vertex shader, and let's go. Can only be applied to values that implement try. Oh. And there you go. Okay, what is the impl type? What? Alrighty, let me try to find. Actually, let me fire up the editor here. I didn't have this problem before, I'm not sure what's up with this. But like, if I remove the import that I have currently, vertex definition, yeah, if I remove that, what's gonna happen here? And if I try to import it now, okay, let me see which one it's importing. Vertex. Let's go up. And yeah, it's importing vertex input, vertex, and vertex definition. Okay, vertex input and vertex definition. Let's import that. It's inside graphics, vertex input. This one. But it still doesn't work out. Let's see. But is this a trait? Consider importing this trait. Okay, so maybe let's say as vertex trait or something like that. These same names are very confusing. But anyway, but now. Yeah, that didn't actually fix the problem at all. Yeah, that didn't fix the problem. What about if I import vertex input? Vertex. Okay, what about that? And yeah, and finally, I need vertex definition. Okay. Alrighty, that was super confusing. But I think this would work now, hopefully. What? Oh, my bad. We don't need vertex input state right now. You know why? Because we're hard coding the vertex like the vertex data in the shaders themselves. So we don't actually need these stuff for now, at least. Though later on when we're gonna have buffers, we're gonna need them. Yeah, my bad. My bad. And I was wondering like why they don't work. Anyways, all right. Damn. Anyway, that was a good start. Stages is equal to pipeline. Well, honestly, let me just copy these stuff. Doesn't really matter. I'm gonna explain these more later on. Vertex shader, fragment shader. Okay. Right now, just group these stages into pipeline shader stages, basically. And now we need to create a pipeline layout. Though in the example right now is actually doing some stuff that we don't have to do right now. So it's adding this pipeline descriptor set layout stuff, but I don't currently actually need this right now. I think I just want to make an empty pipeline for now because I'm not going to be given the vertex data here just yet. I want to show you first the way where you hard-coded data. This function takes 2 parameters, but 1 parameter was supplied, right? So pipeline layout create info. Default is, let me see the default here. Yeah, that's good. Okay. What's up with this? Borrow of moved value. Okay, where it's moved, where it got moved, I think here, right? Let's clone this and let's go. Yeah, and here we need to pass a reference. And that should do the trick. I want to probably clone this here too. Great. So they can share the ownership there. Now we got a layout, an empty layout though, because we're not passing vertex data just yet. Next up is the subpass. Now here the subpass, we need to give it the color attachment formats of the stuff that we want to render to. Let me import this, and here we need to give it swap chain image formats. Okay, because it's the image that we're gonna render to, basically using this pipeline. So we need the formats to match essentially. So yeah, how can I access the swap chain format now? Uh-oh, interesting stuff here. I see. Now the thing is, we need the swap chain to be created at this point to get the swap chain format. But luckily, we have already imposed, we have assumed something that would simplify our code here, which is we assumed that we're always going to be using sRGB format, and if that doesn't exist, we're just going to crash the program. I don't care about other formats. So here it's fine, we could just hard code it in our case. So I'm just gonna say, because otherwise, if I want to actually do that, then I'm gonna be needing to actually create this for every swap chain. Otherwise, well, there is some more advanced ways of actually doing that, like caching and stuff. But anyway, let's just go in and do this. So here we gotta say format, Vulkano format, and here I'm gonna go with BGRA8 sRGB. Okay, lovely. Now we got the subpass. You could have multiple subpasses. Most of the time though, you're gonna have only one subpass, so especially as a beginner. So now we finally create the actual pipeline, and here we could actually return the pipeline here. So graphics pipeline is equal to this, and then here finally we could actually say new, and here we need to pass in an arc device. So yeah, I guess let's just pass in the device, unless if it really needs to be cloned. And then the cache, we could use a pipeline cache to like speed up the pipeline creation the second time the user actually creates or actually launches the application. But for now, we're just gonna go with none, though later on we may want to add this as an optimization. So, and here finally we're gonna add a graphics pipeline create info, add the missing, oh my, okay, never mind. Okay, let's see, how do you okay, anyways, so now what we're gonna need first, we're gonna need the stages. Let me just copy this. And there you go. That's a lot of stuff. Okay, so the stages, there you go, into iterator, and then we're collecting it into a vector. So it needs a vector, or yeah, small vec. I see. And then here the vertex input state. We're not gonna need this currently, since we're just hard coding the vertex data, I believe. Well, at least this one. This one we don't need it. I think it's gonna be none. And what else? Input assembly state. What is the default here? Yeah, this is fine. Topology triangle list. Okay, and the viewport state. This is also probably fine. Yeah, this is fine because we're not gonna have the viewport as static. We're gonna have it as dynamic. So we basically gonna pass the viewport in every frame. So import. Otherwise, we're gonna be needing to actually recreate the pipeline every single time the user resizes the window, which is crazy. And also that would mean that we cannot really reuse this pipeline for every window we have, so for every renderer, I think. So yeah, basically how multiple fragment shader symbols, multi-sample state, we could cover that later on. For now, we're not going to be doing multi-sampling just yet. Color blend state, that's basically to smooth out geometry. Anyways, color blend state, this is, you're going to be needing this if you want to implement, let's say for example, transparency. Though we're not going to care about this for now, the default is probably fine. And the color attachment formats, okay, great. And here where you actually tell Vulkan what dynamic states you need. In this case, we're telling it that we're gonna have the viewport as dynamic state, meaning that every frame we're gonna pass the viewport. So we don't have to like every draw, not every draw, but yeah, every frame basically. Otherwise, as I said, we're gonna need to recreate the swap chain every time the viewport changes, which is not something we would like to do, especially here where we're gonna be reusing this for every window, which could have different viewports. Anyways, so, or in fact probably will. Anyways, subpass, some subpass into here. Okay, great. Now, and layout returns with the specific layout. What? Well, it's not adding anything except for the layout. Interesting. Do we even need the layout actually? Like, is there some default for this? Hold on. Let me see if there is some default function here. That's a lot of defaults. Yeah, but basically I want to see if can we do this, like, hold on. And let me see the default here. Yeah, it doesn't have a default. Okay. Oh, right. Fine. So what's going on here now? Oh, yeah, we need a semicolon there. And I think that's basically it to create a pipeline. And notice here that when we're gonna go out of this scope right here, these shaders would get destroyed, and also this layout. So actually not really the layout. No. The layout is an arc, so it won't get destroyed actually, right? So only the shaders here, right? So result, and let's of course unwrap this up basically, and let's go. Now we got our beautiful graphics pipeline. Let's see if it actually have successfully got created. Great, so we got some panic. What's up? Using physical device, main panic. The pipeline is being created vertex input state, but vertex input state is none. Interesting. And vertex input state, but vertex input state is none. Okay, let me see vertex input state. Yeah, I have removed that, but I guess maybe I gotta give it to them anyway, although I'm hard coding that possibly. Let's see. I'm just gonna go with the defaults, right? I'm not sure why these are options, maybe for extension or something. Anyways, so bindings, attributes, or hash maps attributes. Okay, great. All right, so hopefully this would actually work out. I think it would now. And let's go. Yeah, there you go. Right now we have actually created the pipeline. So in like OpenGL, you can notice here that in Vulkan you pay almost everything up front. So basically this pipeline is just a huge state basically that you make up front, and then you could just reuse it every time you need it for every single frame, and maybe even through Windows. But anyways, right now we're gonna need the viewport and then the attachment image views, which we have already done. So yeah, and what else? Initialization is finally finished. Yeah, so this is it for here for the Vulkan device. Here we're just gonna be sharing this. So graphics pipeline, This may change, of course, later on, but right now we're sharing them between the renderers because they're basically the same. So why bother creating a new pipeline for every single one of them? So yeah, now let's go to the Vulkan render, I believe. But before that, actually, let me add this. Okay, great. What else now? Let's actually, what's up with this? Anyway, let's now create pubfn and Control Alt Shift O. I'm gonna let Copilot do the job. Let's go. And yeah, now let's go to the Vulkan render now. Let's see what I'm gonna need. Okay, so instead of using a transfer command, and actually before that, where I'm creating the Vulkan renderer, I think in the app, yeah, in the visual system, right? So where I'm creating the renderers here, yeah. So we are not gonna need transfer DST anymore because I'm not gonna be using transfer commands anymore. I'm just gonna be using a pipeline, so we don't need this usage flag anymore. Though it would still work with it, but you should make sure to only include usage flags that you actually use for best performance. Anyway, so yeah, and that's it for that one. Now let's go here. So instead of this clear color command that we were using, which is a transfer command, we're gonna actually go with, let's see, I think bind pipeline, but yeah, begin rendering first, yeah. So of course we're using dynamic rendering here, so you gotta have dynamic rendering on, which we have already done. So let's begin. Yeah, as I said, GitHub Copilot wouldn't really help us much with Vulkano, so Control Alt Shift O, and let's go. So begin render. Honestly, let me just copy this. Yeah, fine. So let's just copy this. Okay, great. And yeah, rendering info, import. And well, let me actually try to import everything here. Fix all resolved problems in file. Great. Okay, I'm gonna be explaining these in more depth later on, but for now it's fine. And here we're going to do this. What else? Now we need the attachment image views, which we have already done. It's basically the swap chain image views. So for this, we're gonna go with, okay, swap chain images or image views. Notice that here where we actually need the image views. When we were using the transfer command clear color, we didn't really need the image view. We only needed the images. So here, self.swapchain image views, image index as usize, and this is an arc, so it's not going to be cloning the image itself. This to always make it explicit, I'm going to do it this way. Pretty cool. Lovely. And I need here a reference. Okay, let's go. And that's basically it. So what we're doing here, I'm just going to go through it real quick. We're beginning the rendering. Of course, this is the command, right? In our command buffer. So here we're given a vector of color attachments. Currently, we're only going to be rendering to one attachment, which is the swap chain image. So we're going with one single thing. The Lloyd OP, what happens when you first start the frame to this rendering attachment? At the start, we're going to clear this, meaning we're going to clear it with some color. So in this case, the color here is the blue value. Okay, here we're saying into, because this is an array, and then but this clear value is actually a clear value struct, right? So here we're given also the image view that we're going to render to in this attachment, which is swap chain image views. Now, if we weren't using dynamic rendering, we would have to actually create a render pass and create frame buffers, and every time we create the frame buffers, in every single time the window resizes, So it's just super stupid and a lot of boilerplate stuff. So we're using dynamic rendering, so this is pretty amazing. Okay, next, always when you begin something, always make sure to end it first, so you don't forget, basically. So I'm just gonna say dot end rendering here. And what's up with this? Yeah, because it's a, oh, what? The end rendering like this. Yeah, what's going on? In user, oh yeah, I see. So end rendering, so when you begin something, make sure to end it as always. Now what's up? Now in the middle between these guys, first of all, we're gonna set up the viewport because it's dynamic state, so we gotta give it every single time. So here we could actually pass multiple viewports, but we only have one viewport here. So we're gonna say 0 for the first viewport, and the viewports here gotta be a small vec viewport 2. Okay, so let me just copy this up. Set viewport clone into iter.collect. Okay, now we gotta actually create the viewport. Hold on, where's the viewport? Yeah, it's here. Okay, hold on, it's right here. So let's create it though. I'm not sure why they're creating once. I mean, it doesn't seem like a very heavy object. It's pretty simple, I guess. Is it creating some Vulkan object or is it just a struct? Yeah, I think it's just a struct, really. So it's fine. We could just do it every time. And here we got the extent. Here we gotta pass the actual swap chain extent. So we're gonna say swap chain extent dot into, I believe. Oh no, we cannot do that because, well, basically the swap chain image extent is actually U32, but here the viewport needs F32, so we gotta do it ourselves. So okay, let's get the extent here. So let extent equal to that, and now we're gonna say this. We're gonna say extent dot width, isn't it? Or oh, it's just oh, I see. So just gonna go with 0 as F32 and extent 1 as F32. There you go. And the depth range, we're just going from 0 to 1. This is basically a range, right? And that's it for setting the viewport. Oh, it's cloning the actual viewport itself, which is fine since this is just a simple thing, right? Simple object. All right, great. Well, I mean, instead of cloning, you could just pass it directly, actually. Like, can we do this? There you go. Okay, fine. So we don't really need this weird stuff. Alrighty. No method named end rendering. Yeah. There you go. Now we set the viewport. Next thing would be we're gonna bind the pipeline graphics that we have created. Bind pipeline graphics. Let me just copy these anyways. But actually no, never mind. Let's pipeline graphics and let's say arc clone. And here we're gonna access it from the Vulkan device because this is basically shared through all the windows, all the renderers. But yeah, and then, well, we're gonna make sure to unwrap this. And then we're gonna, like here in the tutorial, they have bind vertex buffers, but we're not using buffers just yet. So right now I'm just gonna go directly and say draw. and I'm gonna draw 3 vertices for a triangle and 1 instance, and 0 for the first vertex, 0 for the first. Basically, we're starting from 0 for the vertex index, which we actually use here. You know, it's like, you see this GL vertex index. We're basically saying like in which number it should start. Like, is it gonna start at 0, 1, or what exactly? But yeah, and anyways, now this is great, and I think that's all we need, really. Yeah, seems like. Now let's see if we got our beautiful triangle or not. Let's see. And there you go, we got our beautiful triangle. But the blue background doesn't really fit so well. So let's actually change that. I like this color. Okay, and let's go. And there you go. But this is not really the color that I expected because of sRGB. Now, basically this clear value doesn't take an sRGB RGB, like basically sRGB, right? It takes the color in linear space. But here I'm passing this as sRGB. I'm expecting it to be sRGB. So to actually get the right color that I was thinking about here, I gotta change this into sRGB value first, then pass it. I'm gonna create an sRGB color, then convert it into a linear value or linear color, then pass it to clear value. Now there's some interesting crate that is quite useful for color transformation, and that may benefit us in a lot of other stuff later on, which is palette. Some crate called palette. Let me make sure I'm spelling the name right. Is the stream fine, by the way? Let's see. Is the stream is fine? It seems good to me. Great. Okay, so let's go to palette, cargo, rust. If you say just palette, cargo. Well, anyway, let's see. It's a color crate. Hold on, let me just search for it. Doesn't seem to find it. Rust color crate palette or something like that. Let's see. Yeah, there you go. So this crate would be useful for color transformations. A library that makes linear color calculations. I mean, we could indeed do the math ourselves. It's pretty easy, but we're probably gonna need in the future a lot more than just, you know, converting between linear and sRGB. So it's fine. Let's just take this crate. Library that makes linear color calculations and conversions easy, and conversion easy and accessible for anyone. Use the type system to enforce correctness and to avoid mistakes such as mixing incompatible color types. It also would like express that we're actually passing here a linear color and here an sRGB, etc. So it would make our code much more nicer. Anyways, so let's add this guy. And yeah, I probably spelled the name right, correct, wrong, sorry. Yep, I did. What's happening here? Cargo add palette. And let's go. Right, it also supports this other stuff. Anyways, so basically here, let me create my clear color sRGB. So actually, I mean, we already have a clear color, really. But let me show it to you here anyways. So basically my clear color, I'm gonna create it in sRGB. So palette sRGB, let's go. And here I'm gonna say from line, let's just create a color new, and I think we're gonna go with 0.1, well, sRGB, yeah, 0.1, I think, 0.1, 0.1. And let's go. Now we got an sRGB color, but why it's saying RGB here? Interesting. Weird. Anyways, and here we're gonna pass in the clear color, though actually I want sRGB-A, not sRGB. And what's up with this? Yeah, here it's gonna take 1.0. Great. Now what we gotta say is, we can say this clear color dot into, I believe. What's up with this? I think you gotta say as array or as slice or something like that. The array. What? I don't remember how did I did it before. Yeah, I want into linear, but let's start with this first. Into. Which one returns a slice or an array? Let's see. What? There you go. You say as mute. Maybe as ref? Yeah, okay, great. But this would actually give us what? Expected clear val. Okay. Into maybe then? What? Try using fully qualified. Weird. Let's see. What about clear color value? And then I could pass it. Oh yeah, my bad. I see. And here we could say clear color. I believe maybe don't into. And mismatch types, clear color, clear value found, clear color value. Expected, oh yeah, okay. And let's give it the clear color and let's convert it into. Okay, so now it works, great. So right now we have just actually the same exact code, but just with that crate. So we're still gonna have that problem, but there you go. But right now the actual solution here is to say, instead of into, I want to say into linear first. I want to convert it into linear space, and then basically convert it into a clear color value. And now this should actually work as I expect it to. There you go. That's the color that I actually expected. Let's go. Nice. Lovely. So now we have a beautiful triangle. Amazing. Lovely. And let's see if multiple windows actually works now, so we can get multiple triangles. Let's see. Alrighty. Yeah, here. Let's say 4 windows. Sorry, just 3. Because these are the secondary ones. But anyway, let's go. Alright, so let's go. 5 triangles. Oh my god, that's another level. There you go. Let's go. Triangleception. Nice. But you can only where's the primary window? There you go. Oh, what? Why can't you close this? What? Are you kidding me? Interesting, why? was that? I couldn't close the primary window for some reason. Very interesting. So this is the primary window. Oh, okay. So I'm not sure what happened there, but there you go. It actually works. Let's go. All right, nice. Now we actually, currently we're just, as I said, we're just like, I don't need this by the way anymore, honestly, for now. Because I'm using Vulkano shaders macro. Okay. So now we're just hard coding the actual vertex data into the shaders themselves, which actually wouldn't work in a real application so well. Why? Well, we do actually want to, like, we don't always know the actual vertex data up front, and we cannot really store a lot of vertices in the shader itself in line. That wouldn't be a good idea. Anyways, so we gotta go into the next level, which are buffers. By the way, can I actually change the version here? Let's see if I can change that without any problems to 460, because that's the last version of GLSL. Currently, of course, the latest, not the last. There you go. Okay, so it works. Lovely, 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 lovely. Let me just, I don't need multiple windows now. Where is it? I gotta clean this up later on anyway. Right now I'm just gonna say 0. Okay, cool. So now let's go ahead and add buffers. And for that, I'm gonna do it in the device currently, because all my windows share that geometry, or at least will share that geometry for now. So let's go ahead and add some buffers. Now there's a lot of ways to make buffers in Vulkano, but I found some interesting way. But well, let me just go with the simple way of doing this, I think, and then we could try to kind of optimize it. Anyways, let's see where to start now. Should I do it before the pipeline or after? Yeah, before. Let's go with before. Okay. So I'm just gonna have the example as a reference here. Where is my example? I don't know where my, oh yeah, I was using this actual thing. Okay, let's go. Alrighty. Okay, where's the struct? So first of all, we need the vertex struct. There you go. In Vulkan, in raw Vulkan, it's kind of crazy to create buffers. You have to care about a lot of crazy stuff, but you don't have to. So all right, back. Let's go. Where is this? Yeah, what I was talking about. Okay, yeah. As I said, in raw Vulkan, it's kind of complicated. Not complicated, but like it contains a lot of stupid stuff that you gotta do. But in Vulkano, it's actually much more simplified. So here's how you create a vertex struct. So of course you create a struct as normal as you would do, but you're gonna have a little problem here. It's gonna say that vertex is defined multiple times, and you know why? Because we have already important vertex here. So what we could do here, we could either change our struct, or we could change this. We could alias this as something else, like let's say as vertex input vertex or something like that. I think this is just a trait possibly, or something like that, maybe. Unused imports. Okay, so does that work? with the alias. I think it's a trait, so it should be fine maybe. Yeah, it's just an alias, so you could rename it however you want. So that's great. Now I think we could actually go ahead and do the thing that we wanted to do. So yeah, we have a simple struct vertex. Now we could actually put some attributes into this vertex, like position. And here it's going to be f32 2. So it's just an array of f32s, like of floats, 2 floats. Basically a vec2 in GLSL. But here, well, I mean, you could just go with this, but we could make use of some Vulkano stuff to actually make it easier to generate the vertex layout, basically. So here what we do is format, and then here we give it the format that we want in Vulkan for this specific field. And in this case, we're gonna go with R32, G32, S float, basically signed float. So yeah, basically red, green. It's not really a color, but like we just use RGBA for X, Y, Z, W anyways. So, and then here it's gonna be S, not plus here. It's gonna be like this. Here we're gonna use signed float. Okay, so 32 bits, 2 components. All right, lovely. Cannot find attribute format in the scope. Right. So let's add the derive. What? Add derive attribute. Yeah, let me see. So hold on. So before that, actually, I guess maybe we need these guys. So the thing is with Rust is the struct fields could be optimized however Rust wants it, really. So you shouldn't like rely on that. But if we say recurrency like this, it would make sure that the struct field positions alignment blah 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 actually aligns with the C struct, just like you have created a C struct with these attributes. The other thing that we're gonna need in a second is derive buffer contents. Now we need to derive this, or otherwise we could derive bytemac pod type in I think 02. But anyways, but yeah, so we need to derive this so we could actually put this in actual buffers in a Vulkano buffer. Basically this would basically make sure that it's aligned correctly, I think, and stuff like that. Anyways, the other thing that we're gonna need to make use of this format attribute, I think, is to add this vertex, to derive from this vertex basically. But hold on, what if I said vertex input vertex here? I think this is maybe, yeah, there you go. So you gotta derive from this too, so you could make use of this format essentially. And you could also get the, let me see, let's see, where is it? So you could make use of another function, I couldn't find it here. Anyway, we'll see later on. So that's it. Basically, this is how you create your vertex struct. Though for other things, basically, if you want, let's say, to just put something in a buffer, then you just derive this and recurrency without the other stuff. Right, this is just for the vertices. Anyways, what is next? What is next? So for now, we're just gonna create a little vertices array. So I'm just gonna copy this actually. What's up with this? Yeah, I shouldn't do this here. I see. But I guess I could say const vertices, isn't it? Yeah, but I gotta give it the type and stuff. But honestly, I want this to be dynamic because I may want to load OBJ models and stuff later on. Anyways. So let's just copy this and to here, where is it? Oh yeah, so okay, let's do it here. Let's do it here. So let vertices is equal to that, and then I'm gonna show you index buffers later on. For now, let's just start with one single vertex buffer actually. And let's go. Okay, so now we're gonna need this vertex buffer. There you go. Let's actually import everything here, fix all. And let's go import what? Vulkano buffer, I think. And there you go. So basically there's a helper method in buffer module. It's called from iter. And you could basically give it an iterator. And it would put the data from the iterator, it would write it into the buffer. But of course, the buffer should be in host. Like, not really should be in host, but it should be like host writable and host. Like the host can actually write to it basically. For example, a device local buffer, where like basically a buffer where it's inside of the VRAM, like the device memory. You can't, like, there is, like, if it's dedicated VRAM, it could indeed be actually writable by the host, but it really depends. Right? But anyways, so here we got the vertex. So you give it the memory allocator, which we have already created, and you give it a buffer create info. In our case, we're only giving it the usage. And here basically it's just an optimization. You want to tell the driver like what you intend to use this buffer for. Though in Vulkano it would give you a runtime error if you don't use it correctly, but yeah. Anyways, buffer usage, vertex buffer, and then allocation create info, memory type filter. Here we tell it like which kind of memory we want to put this buffer in. And here we're telling it to prefer the device memory if it can. And then here we're saying memory type filter host sequential write. Well, this is kind of interesting to explain, but basically would use this for something like a staging buffer, which we're actually going to be doing later on, but it also useful for this case. But anyways, but this probably would go to, well, it could be in a, like, yeah, anyway. So since this is host sequential write, it's either going to be in the device or the host, but it's going to try to prefer the device. But if it can find some data in the like some memory in the device that is accessible and writable from the host, which is not always, which doesn't always exist. Like not all memory is actually accessible and writable from the host in the device, in the VRAM. And even when it exists, it's usually very small, like, I don't know, 256 megabytes or 128 megabytes or something like that. But here we're just telling it preferred device. Vulkano would take care of the rest, basically. So, yeah, great. Otherwise, you could tell it prefer host if you want to. Interesting. Now, since we're going to be using this from the device directly, or not going to be using the staging buffer just yet, I think this is the correct ones, right? Prefer device. Okay. Because the buffers that are in the host and used by the device are pretty slow to access from the device, basically. So you should prefer that it exists in VRAM, basically. Anyways, so that's our vertex buffer. What's next? Well, next we gotta actually care about the pipeline layout, which we actually ignored before. And for that, we're gonna basically create a vertex input state. And the nice thing about Vulkano 2 is that you don't have to worry about layouts. As long as you have done this format stuff and this and derived from this guy, you don't have to worry about it. It can just automate that for you. So here is how to do it. So where it's doing it after the stages. Okay, great. Basically, you gotta say, well, actually, let me just copy it. Let me just copy it over. Let's not spend time here. And there you go. I'm just gonna call this vertex shader actually. So vertex input state, and here we're saying per vertex, and the definition. And here we're giving it vertex shader dot info dot input interface. We're basically like Vulkano gives you a reflection on the shaders, so you could just take the vertex shader it would basically look into the shader and see its layout, and then it's just basically gonna deduce the vertex input state from it, so you don't have to do it manually here, which is nice. Makes a list. Okay, great. Now let me actually create a layout. And now for the layout, we're gonna go with, I really hate to use clone like this. Arc clone. Device, and here let's actually import this stuff. And we need the stages, so after this guy. Okay. So here what we're doing is we're creating a pipeline layout, right? We're giving it the device, then we're giving it a create info. Here though, we're actually deducing the pipeline layout from these stages that we have created from the shaders. So we're using this handy function called into pipeline layout create info, I think. Actually, no, from stages, right? And we're using this into pipeline layout create info, basically. But you shouldn't use this in an actual application. This is just a useful, since we only have one pipeline here. But what you would usually do actually is you would have one layout, which basically describes the interface of the pipe between the pipeline and the shaders. And basically multiple pipelines could actually share the same layout. So when you actually switch the pipeline, like you don't have to switch the shaders basically, but yeah, like you could reuse the shaders for multiple pipelines essentially and stuff like that. But anyways, like multiple resources, not just shaders, I think. But anyways, whatever. So you would usually have in an actual application the layout here, and then you would create all of your pipelines and stuff. Of course, you could have multiple layouts, but here we just have one single pipeline, so we just do it this way, it's fine. Okay, great. What's next? We got the sub as. Now we're gonna add this to here, right? So here in the vertex input state, I just passed default because we were hard coding the data of the vertices, basically. But right now we gotta pass the actual vertex input state. As simple as that. And I think that's basically it here. Maybe. Did I miss anything? Yeah, I don't think I missed anything here, which is pretty cool. Okay, so that's what you do to add that. Nice. Now what's up with this? The memory allocator, where we have moved it here. Okay, let me make sure to clone this. What's up with this? What? Where is the memory allocator? It's an arc, right? What's up? Expected arc, then memory allocator found arc, generic memory allocator. What? Weird. Let me see. Yeah, it's passing the memory allocator. Oh, I think maybe I need to... What? Hold on. That's super weird. So basically without this arc clone it worked, right? Okay. And what this actually takes, it basically moves the arc. So why arc clone doesn't work here? What? This is confusing. Yeah, but why clone works but arc doesn't work? Super weird. Anyways, Yeah, fine, just use this clone though. Let me make sure it's actually doing the correct thing. Yeah, it's giving a new arc. I'm not sure why it's different here. Super weird. But anyway, this should fix it. And what's next? Now we gotta actually give a reference to our vertex buffer too. So typo invert subpass layout vertex buffer. Should we use an arc here? I'm not sure if we really should use an arc here. Probably doesn't have to. But anyway, it's a sub-buffer vertex. Okay. Let's just pass it as it is right now. So sub-buffer. So vertex buffer. It's going to be a sub-buffer of... You're going to also notice one other thing about Vulkano is that like your buffers are typed in like raw Vulkan, which you just like... It's just like a bytes and you gotta figure it out, and you also gotta be careful about alignments and stuff. But yeah, in Vulkano everything is done for you. Well, not everything, but you got the point, right? So here I think we gotta do it like this, and struct takes one generic. Okay, so this should do the job, I think. Vertex buffer, and then here we could just pass it up, add missing fields, and there you go. Now Control Alt Shift O, and there you go. Let's go. Now let's go to our render right now. Let's make sure though this actual buffer is being done. I may have missed something, not sure. Yeah, I probably did. What I have missed. An error current bound graphics uses vertex buffer by... Yeah, because we haven't bound the graphics, the vertex buffer yet. So let's go ahead to the Vulkan render right now, and where we're binding the graphics pipeline. And let's see, so we gotta also bind basically the vertex buffer. There you go, bind vertex buffers. So after this, we gotta bind the vertex buffers. And here, notice you could actually give it multiple vertex buffers. And hats. Sabahul khair. Welcome to the live stream. How is it going? Bind vertex buffers. Here we gotta give it vertex bind, first binding. Then here we gotta give it a collection of vertex buffers. Now in this case we only need one buffer, but you may need multiple. Like currently basically we're gonna have all our attributes in one struct, so in one buffer basically, but you could have like multiple buffers and like basically instead of interleaving all of your vertex attributes in one struct and in one buffer, you could have multiple buffers, and for example each buffer would have like one attribute, so they would be together. Now that would be a good idea honestly to separate the vertex positions from the other attributes and interleave the other attributes. So for Android, like mobile phones, like actually touch GPUs in general, which most mobile phones uses for various cases, it's actually better to separate the position attribute from the other attributes. Why? Because well, there's a stage or phase called binning that these kind of GPUs does at the start of your graphics pipeline, which is like basically your screen would be, or your frame buffer should I say, or whatever, your let's say your window, okay, is separated through multiple tiles, and basically it have to figure out which triangles or which primitives it would draw on each tile basically. So it does a first pass to just go through all the positions. So now if you interleave all these attributes, it's not gonna have like if you actually store just the positions packed by each other, you're gonna have better cache locality in that phase, basically. But yeah, anyways, let's just go with one vertex buffer for now, which is gonna be self dot Vulkan device, I think, dot vertex buffer. Let's go. But what this requires, the tray bound is not satisfied, is not implemented. I guess we gotta clone this. It should be fine because I don't think it's gonna clone the vertex buffer itself, because that's just like a sub buffer. It's just like a view to the, like a slice to the buffer itself. But let me make sure that's the case, honestly, so we avoid any crazy stuff here. That would be funny if it actually cloned the whole buffer. Let me see, fn clone self.parents.clone, but what is parent? Sub buffer parent, okay. Arc arena, what? Or a buffer? Yeah, just an arc buffer, I think. So it wouldn't actually clone the buffer itself, it would just clone the, yeah, so it's fine probably. So yeah, we're just cloning it here, and then we're gonna remove the errors, of course. What's happening now is private. What do you mean? A Vulkan, I guess maybe I know why. I think maybe we need to make this vertex struct public. Maybe that's why. Yeah, so we could access it from here. Let's go. And I think that's basically all we need to use a vertex buffer, and cherry on top would be to just here use right now self.vulkan device dot vertex buffer dot len. So we basically derive the length, like how much vertices from the buffer itself. So yeah. So expected U32 but found device size. Yeah, fine. So add save cast to U32, and this should be the exact same thing, but now oh, did I change the shaders? I don't think I changed the shaders yet. Oh, I changed them yet? What? Yeah, there we go. So like the same thing, but we're using buffers right now instead of hard coding them into the shaders. But let me make sure I have actually changed the shaders. No, I haven't. And it still worked. Okay, that's interesting. But this is not how you do it though. Hold on. I'm gonna actually copy here the shader that we should actually use, because this is basically just hard coding the vertex data here, which we don't want right now since we're using actual buffers. And ever tried vertex polling binding? The vertex is just like a uniform. You need the code for uniforms. Other way, actually it works better on video card, and you can access other vertices if you wanted. And you can access other vertices if you wanted. Ever tried vertex polling binding just like a uniform? I haven't tried it before. But the problem with that, possibly, can you use it with an index buffer though? I think that would possibly cancel that vertex cache of indices and stuff, right? Yeah, I think so. But that should probably work, though I'm not sure if it's possible with Vulkano just yet. It probably is, but yeah. We are deep inside the Vulkano now. Okay, alright. So the code right now that we actually gotta use here in our shader, which is this. So instead of this, which basically hard codes the data, well, let me show you actually the changes that is needed here. So we don't need these hard-coded data anymore. This would stay the same, but we don't have colors yet. Though we could add them. Hold on. Let's add colors. Since we have gone with them, let's add them. So let's go back to our vertex layout. It's actually pretty easy to change the vertex structure with Vulkano, thanks to all these reflections and stuff. So you would just say color. And well, by the way, this is actually expecting a vec3, is it? Let's use vec3 for position anyway. And here, since we've done that, we gotta add the blue component too. And we're gonna have the same thing with the color, really. And that should do the trick. Your Discord invite is invalid, by the way. Oh my god, what? Like, I have just updated it recently. How is that the case? Are you sure about that? Let me see. How do I do that? Let's see. Where's my link? No, it's 2 weeks by default. No, I have changed that to like which link is in this video, in this live stream, because I have just updated it just recently. Though let me know. Can someone also some other person also tries it, see if it works. But anyway, so right now we got position and color attributes. Nice. So how can I, like, what else should I change now? Let's see. Yeah, we just should change here this guy. So of course we're gonna add 0 here. Okay, and finally we gotta add the color. So for the color, let's go with 1.0 for our. Now the thing is, in shaders you don't have printf, you don't have printing stuff, so you can't debug that way, right? So how do you debug? Like in shaders we mostly use colors to debug. So here, for example, I could put my first vertex color as red, and then my second vertex as green, let's say, and my third vertex as blue, right? And now I'm gonna know which vertex is first, which is the second vertex, and which is the third vertex by their color. Basically, this is how you debug in shaders. You use color, for example, to debug stuff. It worked now, but gave me invalid 2 times. Weird, super weird. I have just updated it recently because someone else have told me that it's invalid. But I say that it should be forever in Discord, so I'm not sure what's going on with Discord. Anyways, so this is great. Now I think this is all we really need. If we weren't using Vulkano though, we're gonna need some other crazy stuff, like we gotta change the layout and in several places and all sorts of weird stuff. But yeah, I think that's all you really need in Vulkano to change the layout and to add a new attribute. Now let's actually change our stuff here. So we don't need these anymore. And here we're outputting this color into the fragment shader, because basically our buffers, our vertex buffer is only available to the vertex shader, right? Now if you want to pass some data into the fragment shader, we gotta do it through output variables. Like here we say an out, and then we're given a location equals 0. Now it doesn't matter the actual name of the variable. What matters is the location. So here you have to create a matching pair in your fragment shader with the same location. So it maps to it basically. Otherwise it wouldn't work. So the fragment color, as you can see here it's an output and here it's an input, but they have the same location. So they get connected together. It's like a USB. Anyways, and you're gonna notice that the locations are in different namespaces. So like here, this output is also location 0, but they don't catch, like they don't go against each other because they are in different namespaces, right? So yeah, that's basically it. Now what's up with this? And also notice this is that Vulkano, yeah, it actually compiles it at compile time. It compiles the shaders at compile time into Spurvy, and notice that it gives me also the error inline, which is pretty interesting. Lovely. That's pretty cool. Okay, so now what I gotta do, so instead of positions GL vertex index, right now I could just take it from my, well, I gotta add I think a layout location 0. So out and this point input, I don't actually remember how you do in GLSL. Hold on a second. Let's see. Yeah, here's the vertex. So you just say in vec2 position. Okay, in vec3 position, right? And then since we also have the color though, so we gotta say this, and we're gonna have color here. Both, and of course it gotta have multiple locations, like this have 0 and this have 1, because the first attribute is position and the second attribute is color. And now what we gotta do here, instead of positions GL vertex index, we gotta go with the position that we got from our buffer, and here instead of colors GL vertex index, we gotta go with our color. We gotta, basically here we're passing it to the fragment shader essentially. So like frag color, which is this output here, to the fragment shader, we're setting it to our color that we got from the buffer. And this should actually work. But yeah, vec4, this should take 4 values. And here we're actually passing it more than that. So, and there you go, this should work out. Lovely. Is there anything I have to change here? Frag color, out color? I don't think so. This is basically the attachment that we have created. So we have only one attachment in our pipeline. So it's in location 0. If you're gonna have like multiple, actually sorry, this one, I'm talking about this one, out color, it's the output. So here you actually output into a render pass attachment. Well, we don't have a render pass here, but we're using dynamic rendering. Is gonna be yeah, in begin rendering command. But anyways, so like you could have multiple output attachments, so you're gonna add them here. Anyways, so this should actually work great right now if I didn't miss anything. And it should also have colors just like before, but right now we're using buffers. Great, lovely. Let's go. So it actually works out. Amazing. And right now we could add multiple windows. Let's make sure that also works, because why not? We have added them, so let's use them. Let's see, where did I, yeah, here, let's say 3 windows. And there you go. And all of our windows are using the same pipeline, the same vertex buffers. And there you go. And you could actually do something crazy like this. So yeah, you could create multiple windows however you want. So that's very cool. I'm not sure, sometimes it doesn't want to close, but I can try to fix it later on. Anyway, so have fun. Thank you so much. Okay, so now what we gotta do next? Well, next I'm not really sure what to do. I think let me try to use sub-buffer allocator. No, yeah, I know what to do next. Yeah, I just forgot. So right now, currently, if we go back to our buffer code, where's our buffer code? Where is the buffers? Vulkan render or Vulkan device? Yeah. So let me see, hold on a second. Okay. So currently our vertex buffer, what we're doing is we're preferring the device, but it should be host writable. So it would probably be in the host, or otherwise it would be in the device. So this is really not the best solution to do it this way. So what we should actually do is we should create a dedicated, not a dedicated, but like a device local vertex buffer, like a buffer that would be in the VRAM, right? But the problem is, if we done that, we probably wouldn't find it in the, like we can't write to it from the host, right? So what we should do, we should basically, create a vertex buffer that is actually a device local, but then to actually write to it, you create another buffer called a staging buffer. And then that staging buffer would be like host writable. Then you would write to that buffer. And then in a command buffer, you would tell the GPU to copy the data from that staging buffer, which is host visible, that you can write to it from the host. And you copy it to the device local buffer, which exists in VRAM. Basically, I'm just going to give a little simplification here. What we're doing is we're creating a buffer in VRAM, right? But the thing is, we cannot access that buffer in VRAM from our CPU. So we create a second buffer called a staging buffer in the RAM, not in VRAM, but RAM. We write that data to that staging buffer, which is in RAM. And then we create a new command buffer that we're going to send to the GPU. And that command buffer will basically copy data from the staging buffer, which exists in RAM, to our vertex buffer that exists only in VRAM, because basically telling the GPU to copy the data, because the host can't actually access that buffer because it's in VRAM. But yeah, hopefully that makes sense. But anyways, though before that, honestly, let me just create an index buffer first, and then we're gonna go to the next stage, I think. So for creating an index buffer, it's actually pretty simple. It's very similar. Just instead of vertex buffer, we're gonna call this index buffer. And here, same thing, but we're gonna need some indices. Now, first of all, why we need indices? Well, we basically need indices when we have like shared vertices. Like, for example, let's see, like basically in a mesh, you have a lot of triangles, and all those triangles share a lot of vertices, or at least most of the time share a lot of vertices, right? So instead of duplicating that vertex data every time for those shared vertices, what you do, your vertices or your vertex buffer would only contain the unique vertices, which means you wouldn't have multiple vertex data in there. You would only have the unique vertices. Like if there is, like, let's say vertex is shared by multiple triangles, let's say 5 triangles, then instead of putting that vertex 5 times in your vertex buffer, you only put it 1 time. But then in your indices buffer, what you have is every time you need to share it, you just tell it the index in the vertex buffer, basically. So like, yeah, basically your vertex buffer contains the unique vertices, then your indices points to those vertices through an index. Hopefully that makes sense. Anyways, so here we have it pretty simple. We only have 1 triangle, though honestly an index buffer doesn't really make much sense here because we're not sharing any vertices at all, so it's kind of just an overhead in this case. But later on we're gonna have a lot of vertices when we try the actual meshes. But anyways, here, yeah, we got indices. Now we got a lot of choices on the index format too. But in my case, for now, I'm just gonna go with U16. If U16 is enough for your mesh, then you should probably go with it because it's much more packed, basically. But you can only go up to 65,000 vertices. But if your mesh is over that, then you gotta use, let's say, U32. For now, let's just use U16. And right now, we're gonna create an index buffer. But here, the buffer usage, we gotta make it index buffer. We gotta tell the driver that we're intending to use this as an index buffer so it can optimize things up. And then here, we're telling it preferred device, so sequential write just before, like before. Here, we're gonna tell it the indices data, basically. And this should actually be good enough, I believe. That's how you create an index buffer. Next up is, well, we actually need to store this so we could actually reference it from the renderers. So let's see here, yeah. we're gonna add in here index buffer, and here sub buffer vertex array, basically. And let's go. Now we just gotta add this here. Where is it? Here. Let's add the missing fields. Ooh, what is different here? Did I have done something wrong? Oh, it should be U16, my bad. I see. Not vertex here, it should be the actual index type. But honestly, let me just say here const index type is equal. Oh, can I actually do that? I don't think I can. I thought I was in Zig or something. But no, I don't think I could do this. Yeah, you could use generic, but nah, let's not go that way for now. Let's just say U16, okay? And in the other place, you gotta say this add missing field. What? What's up? What's up with this? Hold on. So sub buffer U16. Okay, what I've done wrong then? Weird. Okay, add this. Index makes sense. Index buffer. Why couldn't? What? I'm probably doing something stupid here. Yeah, probably. I'm not sure what's up with this. Oh, no such field. Index, what? I see. Yeah, I said that. Probably doing something stupid. Yeah, I'm actually doing something stupid. Anyways, so that's basically it for that. Now, in our renderer, we can go ahead and we can bind the index buffer. Bind vertex buffers, then we could like bind the index buffers too. And here, we need to give it the index buffer. Self.vulkan device .index buffer, because we're sharing the buffers through all the devices, so we could reuse them basically. What's up with this? Yeah, I didn't add the getter. Okay, see. Control Shift O. Sorry, Control Alt Shift O. And create it for me. Let's go get up Copilot. This is the only job it has. Anyways, .index buffer. GitHub Copilot currently is only useful for making getters. Anyways, the trait bound is not satisfied. What's up with this? I guess I gotta clone it, yeah. And then what? Yeah, just unwrap this, and we should have the exact same result, but right now we're using an index buffer. Okay, great. Now let's actually try to do the stuff that I was talking about before, which is actually creating buffers in the VRAM, making sure they are in the VRAM, and then using staging buffers to copy or transfer data to the VRAM. So let's go ahead and do that. Now, we cannot use from iter anymore. So basically what we're gonna do, let's see, instead of from iter, we gotta do new, I think new sized, because I know the size. Actually, no. New slice, probably new slice, and we gotta go with And right now we're not gonna give it the data itself. We're just gonna give it the length of the data. So indices.len. And what's up with this? Add save cast to device size. Import. And there you go. But right now I gotta make sure that it's preferred device, and I don't need this host sequential write. Just gonna tell it preferred device. I don't need to write to it from the host now. In fact, I shouldn't do that now. Though instead of preferred device, I could even go further and say this instead, just to make sure that it's actually required. I could say required flags and then say which flags here? Memory property flags. And I could make sure that it's actually doing it, not just preferring it. Memory type, is it, or what? Bro, I forget a lot. Memory property flags, okay. Memory property flags, and let's go here. Gotta say device local. Basically, we're gonna make sure that it's actually sitting in the device local memory, which can't be accessed by the host. So missing fields, initializer. Yeah, for the other sub, just say default. Okay, and that's it. Yeah, pretty much. Lovely. That's how you do it. Now, pretty much similar thing for the vertex buffer. Index buffer, and here, oh, what I'm doing, oh, here, this should, oh, yeah, this should be vertices, .len, and then what, and this should be vertex buffer, and this should be vertex buffer, right, okay. And here also device local. Okay, lovely. Now we have created our device local buffers. Now we gotta create a staging buffer. And let me see how I'm gonna do this. Now there's a lot of ways to do this, but I'm gonna start with the simplest way, which is to just write, like, make a staging buffer for every single buffer. So like here in this case, for the vertex buffer and for the index buffer. So let's make a staging buffer. So I'm just gonna copy this, and let's make a vertex staging buffer, because we cannot write to the vertex, device local vertex buffer directly, or any buffer directly, right? So vertex staging buffer, what we're gonna do now? Now you're gonna notice that it needs the annotations. Actually, we don't really need that. Yeah, for this, I'm just going to use the code that we were using before for the buffers. So let me just copy it here, actually, which uses from iter, basically. So here's what I could do. So I'm just going to say vertex staging buffer. Basically, the code that I was using before. But, I mean, I'm not sure if I want to prefer the device or the host for a staging buffer, honestly. It should both work, but I'm not sure. Like, I never really questioned. Let me see, hold on. Is device or host better for staging buffer? I'm really not sure. Though the example seems to probably go with device anyway. Actually, the example doesn't contain that, but anyways. But it's probably gonna be in the host, honestly. But I'm not sure. Staging buffers give you the ability. Let me show you what I'm reading. Anyway, let me see if this is any useful for me here. I'm not sure even if this is the question. Does staging buffer have better performance than host visible and host coherent? I don't think this is my question. I'm not sure. I'm gonna oh well, let me see what this guy is doing. Wait, where he's doing it. Abstracting buffer, using staging buffer. Okay. This is raw Vulkan, the Spartan way. Okay, let's see. Device local. No, here. He's basically saying property host visible, host coherent. That's not really telling me much about that. Anyway, I'm just gonna go with prefer device for now, or probably prefer host. Anyway, we'll see. But I'm gonna keep this host sequential right essentially. So yeah, let's just go with this. So later on I'm gonna research on which one is better, but anyways, but both should really just work. Index staging buffer, and here we're gonna go with indices. I don't need these in wrap, I could just say this and this. And here we gotta actually clone this guy. Not sure why our clone doesn't work for this one, but let's just go with clone for now. Actually, do I really need to clone it again? Yeah, I do. Okay, great. Now we got both staging buffers filled with the data that we want, and creating the other device local buffers. And then we gotta actually create a command buffer here. And to do that, we gotta say let builder, well, let's say command builder or something like that, I don't know. Anyway, you gotta say auto command buffer builder, then primary. We want to create a primary command buffer. Now there's two types of buffers or command buffers. There is secondary and primary command buffers. Now primary command buffer, it is the one that you actually submit to the queue. Secondary command buffers is the one that you can actually execute from primary command buffers. How I'd like to think about it basically is like that the primary command buffer is basically like a device program or device instructions that you send directly to the device to execute. And then the secondary command buffer is just like a function, you know, where you could like reuse it in every single primary command buffer, like execute it from the primary command buffers. Anyway, we don't care about secondary command buffers. We're gonna go with primary here, and we're gonna say what primary returns. Yeah, it actually takes some arguments. Hold on. So we need the allocator first, and we have already created that. Let's go with command allocator. It's actually command buffer allocator, but I've just called it that. And then here we need the Q family index. Here we are in the Vulkan device. So let's say a Vulkan instance, I think. Where we are right here, let's see. Yeah, we got the Q, and yeah, we got the Q family index here. Okay, let's just pass the Q family index, and then the usage, command buffer usage. Now there's multiple submit, one time submit, and simultaneous. We're just gonna submit it once, so one time submit. And then this gives us a result actually, and there's a problem here. Command allocator, expected but found arc. Okay. So let's actually give it, I guess, a reference, or yeah. Okay, so right now we created the command builder. Now let's actually give it our command, which is actually pretty simple. I'm just gonna tell it to copy the buffers from the staging buffers to the actual device local buffers. So here basically we're gonna be sending some instructions to the GPU to copy the buffers, and so of course we gotta use a command buffer for that, and we gotta submit that command buffer to a queue to execute it, and then we're gonna wait for that command buffer to finish execution. Otherwise we would have a problem. We gotta make sure that the GPU finish execution first. But anyways, So here command buffer info, and here we're just going to use a helper function here called buffers, and then we're going to go with the source buffer. So here you tell it the source buffer. Notice though one thing is that these guys take sub buffer, not an actual buffer. And even when you create buffers, you don't get an actual buffer, you just get sub buffer. Why that's the case? But basically in raw Vulkan, every time like you give a buffer to some command, like copy buffer here, you actually give it a offset, and then you give it the size, like how much data you want from the buffer and the offset to that buffer. So it's basically a slice, right? But in C you cannot actually do that. You cannot express that basically because there's nothing like that basically. But basically in Vulkano what they did, they do have a buffer. They also have a row buffer. And they also have, now a row buffer is just like bytes. It's just like raw Vulkan, you know. It's just bytes, it's not typed basically. And then you have a buffer, which is an actual buffer. It just wraps the raw buffer, but it's typed. So like you know the type. So like here it knows the type Vertex, it knows that it is U16. So this helps with a lot of things, with type safety, and it also helps with alignment requirements. Now if you ever have dealt with raw Vulkan requirements and alignment issues and stuff, you're gonna know what I'm talking about. But anyways, so yeah, there's a lot of like layers of abstraction you can use. And then there's subbuffer, which just wraps a Vulkano buffer, but like it's kind of like a slice, like a Rust slice. It also contains the offset and the size of data that you're interested into. So in here, for example, this new slice, it just gives you a subbuffer that spans the whole buffer, right? And yeah, stuff like that. But I'm gonna show you where this subbuffer would be useful in a second when we're gonna optimize further. But we'll see. Anyway, for now, let's just pass in the source buffer, which is we want to copy the data from the staging buffer. So from the vertex staging buffer to the the vertex buffer. And yeah, let's see. Cannot borrow. What's up? What's going on here? Okay, and yeah, let's make this mutable. Let's command builder mutable. And that's basically everything we need. Only one, actually not only one command. We're gonna need the second command now, which we're gonna copy from the index staging buffer to the index buffer. So 2 commands. And then right now we're gonna actually build our command buffer from the builder. So command builder.build, and we're gonna see if there's any errors, and then now we got an actual command buffer that we could actually send to the GPU to execute. So here I don't actually remember how do you do it in Vulkano, but I think you do need to say sync or something like that. Let me see the reference here. So yeah, I think it's sync now, I believe. Let me see. Yeah, I think it's gonna be sync now. Okay, let's see. So sync now. I believe you give it the device. And that's it, I believe. Now let me try to find where I can import this. Yeah, sync Vulkano. And this would give us now. Now we can basically go ahead and say, then execute, I believe. And then we give it the queue that we want to execute this in. Righty, we're gonna go with our queue. Yeah, I already have the queue actually. There you go. And then we're gonna give it our command buffer that we want to execute. And this method takes, there you go. And what's next? I think a flush and stuff like that. Yeah, then signal, fence, and flush. So we gotta tell it to signal a fence. Now in Vulkan there is two types of synchronization primitives, I believe. There is a fence and a semaphore. Now you can use a semaphore to synchronize between queues, and even inside the same queue, but between, you know, multiple submissions. And there's also a fence which you can use to, like, basically you could think about it as that semaphore synchronizes GPU to GPU stuff, but fence synchronizes between the CPU and the GPU. So we could, like, and here we actually need to signal a fence, so we could actually wait for it in here, the CPU, before going ahead and creating the other stuff. So that's basically it. So now here, then execute, then signal, fence, and flush. So first of all, we're gonna unwrap, then signal, fence, and flush. Now this would actually give us a future. This is async. We could use async with this. So fence, or let's call this buffers upload future, I believe. Now I don't understand Vulkano synchronization very well until now, and actually it's gonna change in the next version, I believe, maybe, but anyway. Now this gives us a fence signal future, and then what we could do is wait for this to end. Like we could say buffers upload feature dot await, but right now we're not in a async environment just yet, so we can just say dot wait. So we're just gonna yield the thread until the thing ends, and here we can give it a timeout. In my case, I'm just gonna say none, no timeout. So like, yeah, and here and use the result. Okay, so we're just gonna wait for it, though I don't really need, I mean, at least from my understanding currently, I'm not sure, like, I'm not sure when it's gonna start the submission of this future, like of the command buffer. From what I know, for futures, they're kind of lazy. Like, they only start executing when you actually await them, like when you actually wait for them, when you consume them. But maybe this is not the case here. I believe it's probably gonna go into actually execute, and then I can wait for it whenever I want, but I'm not entirely sure. Though we could do a little thing. We could try something here, which is, let me grab my vacay config. I'm gonna make sure that is the case actually. Let me just see. API dump, and then I'm gonna make a breakpoint here after this guy. And then I'm gonna go into head. Oh, we have this other stuff that we have to take care of first. Okay, good, fine. Let's see. Buffers from iter. So we got index, vertex, staging buffer, borough of moved value. Yeah, let's actually create these guys first. And do I have anything there? Okay, never mind. Let's just create these first, because just getting the length wouldn't move the data. So we could do that first. And that should possibly work out now. Maybe. Let's see what I was missing again. Yeah, here we gotta actually clone this. Just not implement the copy tree. What do you mean? Value, oh, it's moved before. Oh yeah, here, okay. So let's clone this device. Righty. You need to give a reference. What about now? Come on, bro. Then execute q.clone. Okay, where this is happening here, because it got moved in line 106. 100. What? value moved here in 207. Okay, let's see. Okay, let's actually clone this guy. Arc clone Q. And what about now? Come on. Vertex buffer, where's it got moved? 265. What? 200, okay. Here. So we need to clone this guy too. Of course, we're cloning the arc to increase the ref count. Expected subbuffer. I'm not sure why this arc clone thing doesn't work sometimes. Let's just say clone. Where else? Let's see. Index buffer values after being moved. Where it got moved? It doesn't say where it got moved. Values here after move. Move occurs into number 2. The index buffer, okay. Let's just clone this. And let's try now. There you go, we got some problem here. Unwrap on an error. Does not contain transfer. Oh yeah. Yeah, so basically Vulkano also does its own runtime validation. So it would stop you in your tracks if you do something wrong, like here, for example. So what you should do here, it's basically telling me that I forgot to add the buffer usage transfer SRC, which you should for best performance, because here I'm transferring data from this staging buffer. So I gotta include here buffer usage transfer SRC for the index for the staging buffers. So because we're gonna be copying data from them. Index vertex here too. And we also need the transfer buffer usage, but DST, destination basically. This is source and the other is destination. So for these guys, we're gonna go with transfer DST because we're gonna copy data to them. Oopsies. And there you go. This should do the trick. And let's see. Yeah, right now we have hit this this breakpoint. Let's see what it's doing. Yeah, I don't think it executes it just yet. Yeah, I don't think. No, doesn't execute it just yet. Okay, what if I done this buffers deployed feature dot, so there's a wait, which I don't want to do just yet, because while this is going, I want to do some other stuff before actually waiting. Maybe flush. Maybe flush, let's see. Because I don't want to wait just yet for it to end, because I'm not going to be using the buffers just yet. So I could basically, while this is uploading to the GPU, I can do some other actions, some other stuff. Why this is not doing anything just yet? Interesting. Weird. I don't know. But either way, for now, we're just gonna skip this. I'm gonna see later on how to do that, but basically my idea was that I would tell the GPU to execute this, And I'm not gonna wait just yet. I'm just gonna create my pipelines and stuff and do some other things. And then I could, when I actually need them, I can say just wait for them. So here I can say fence future, I think, or what was it? What I called it? Buffers upload future. Here I can await them, but I don't have async just yet. Later on I may show you how to do that. Right now let's just yield the thread. So we're gonna wait for the GPU to do the upload of the data. And yeah, that's basically it. Though I really would love to actually start it before doing some other stuff. But anyways, right now, did I miss anything? Let's see. Did I remove that breakpoint that we had before? Yeah, I think I've done it. And yeah, that should do the trick now. And we don't need the staging buffers after the upload of the data is done. We could just remove them, and in fact this would be done for us because we're using RARI, like Vulkano uses RARI. So once they exit the scope, it would just get destroyed. So that's lovely. Now let's just go ahead and run this, and it should be the exact same thing, but right now we should have the vertex and index buffer. Oopsies, I left the API dump going. Let's just go with validation. And yeah, right now I should just have the same result as I said, but right now we have the index buffer, and we're sure that the index buffer and the vertex buffer would always be in the VRAM, and we're using staging buffers to actually upload the data. Lovely. That's basically how it's done. It's pretty simple. In raw Vulkan though, you gotta care about a lot more than this. It's crazy. But anyways, so that's pretty cool. Love this. Okay, now let's try to optimize this a little bit even further. So, okay, let's see. So right now we're actually creating multiple staging buffers to upload the data. Now, the next thing that you may want to do to actually optimize this a bit further, which is to create one staging buffer, and you would copy both all of your data into it and then submit it at once. So let's try to do this. Now, instead of creating multiple ones, you're gonna create just one. So let's say we don't want this anymore. Okay, and let's see. Now this is just gonna be a staging buffer. Okay, and here, actually, by the way, one thing. Let me go back. I have missed one thing, which is that for a staging buffer, you don't need to say, in fact, you shouldn't, because we're not going to be using the staging buffer itself as a vertex buffer. We're just going to be using it to transfer data, to copy data from it. So we don't really need this usage for best performance. Let me just make sure this is actually working out. Yeah, there you go. We don't need that flag. And now let's just go to whatever I was wanting to do. So now we don't need multiple staging buffers. We're just gonna have one staging buffer, right? And here we're gonna say, now instead of from iter, I'm not gonna say from iter because, well, the staging buffer, I just want it kind of like just bytes, not really typed, because I want to like copy to it multiple stuff. So what I'm gonna do here, I'm not sure if I remember how to do this, but let's see. So new sized, I believe, new and sized, actually not sized, new slice, I believe, and then we could give it the length. Now I'm probably gonna have this as just bytes. So I guess what I could do maybe here is say U8 maybe. I'm not sure if this would actually work, but let's see. And then here we could say vertices.len. Actually, let's say std-mem, because I don't want to get the length of how much vertices there is, but I want to take how much bytes there is. So std-mem size of val, then here I could give it the value, which is my vertices basically, and then I could say plus the size of the indices. So here we need a reference to it actually, and then we could go with indices here, indices, and that may work. I'm not sure, we'll see how it goes. Add save cast to device size. Though this is not the best way to do it, but I'm just showing you and seeing if this would actually work. Let's see. Let's go. There is a much easier way to do this in Vulkano, and much safer way, because I'm not sure if this would actually work out with alignment actually. I'll have to see about that, but anyways, let's see if this would actually work out by any chance. So buffer new slice UH, okay, with that length. Now we gotta actually copy data to it. How are we gonna do that? There is map slice, okay. Maybe map slice. Return the map pointer to the range of memory of slice. The sub buffer must fall within the range of the memory mapping given to map. Okay, I don't think this would work since we gotta care about alignment possibly here or something like that. But yeah, anyways, let's see if this would work anyway. Data. Okay, we got a mapped slice right now. It's not null, can't be null. Okay, now how do we do this? Let's see. std, I guess we gotta use std-mem copy slice, actually maybe slice, yeah. What? Oh, what? Weird. Let's see, data dot, oopsies. Map address creates a new pointer by map itself. Hold on a second. Okay, back. Well, I don't think this would actually work. Let's see. Cast map address. I've done this before though, but creates a new pointer with the given address. Don't remember which function I used, damn it. Maybe right? Yeah, possibly. But I do have... Maybe that's what I actually used. Let's see. This is actually a guard. And I believe now I could say... Now this gives me a buffer write guard of U8 of a slice. Right, and then hopefully I could copy data to it. Yeah, copy from slice, there you go. Copy within. yeah, copy from slice, and then I could copy from, let's say, vertices, I believe. But I gotta cast this into bytes. Not sure if you could do this without bytemuck. I don't think you can. Yeah. So let's get bytemuck. Cargo add. Oops. Yeah. And let's see if this would work. Cast slice, and we're gonna give it the vertices. So it will basically cast it 2 bytes. And let's go. This should be mutable or what? Cannot be borrow mutable. Oh yeah, it should be mutable. Okay. What is up with this? Trait bound vertex pod is not satisfied. Yeah. Now instead of buffer contents, honestly, I gotta use pod. Bytemuck pod. And bytemuck bytemuch. Bytemuck zeroed, I think. Zeroed, I believe. But the problem with this is that it doesn't exist, because you gotta make sure to add a feature called derive, I believe. And let's see. So bytemuck zeroed. Okay, let's see right now. Bytemuck zeroed or what? Weird. Anyway, what about bytemuck pod? Okay. And now we cannot use buffer contents anymore. Bytemuck pod is enough, maybe? Is not satisfied. Okay. So bytemuck zeroable, actually. Bytemuck zeroable. Okay. Hold on a second. Okay. Zeroable. Let's go and let's see what's gonna happen here. Okay, it should also be copy. Sorry, copy like this. Clone and copy. Yeah, as you can see, this is hairy. This is crazy. Let's see if this actually would work by any chance. Anyways, so how to do this actually? Let's see. Index staging buffer. Yeah, I was here. Okay, great. So now we could actually copy from slice the vertices. Great. And now I want to offset this by indices, by vertices, sorry, by vertices dot len. I'm probably it's probably not gonna work because of alignment, maybe. But anyways, let's see. Vertices.len. Now, basically, I'm offsetting this by vertices.len. And then we could copy from slice and cast bytemuck cast slice, right? Indices. I'm really not sure if this would work, but let's see. And yeah, that's basically it. Let's call this writer or whichever. But basically in Vulkano, like, it makes sure that writing and reading data to a buffer is safe by making sure, like, for example, if the GPU currently is working on some buffer or writing to some buffer, you can't actually write to it too. Like, it's kind of like a RW lock, I think. Like, it makes sure that like you wouldn't write to the buffer in multiple places at the same time, you know. So it's kind of like a RW lock, I think. Anyways. And then copy from slice, I really don't know if this would work. Let's see. Okay, so right now we have copied the data to the staging buffer. And now what's next? Now we're gonna say staging buffer. And now we're gonna slice it, I believe. Here I gotta give it the range. So I'm gonna slice it from 0 up to vertices.len, I believe. And then what's up with this? Oh, it should be as device size, I believe. Yeah, let's find out if this would work by any chance, but I think it wouldn't because of alignment problems. Range. There's probably a better way to do it in Vulkano, but anyways. Okay. Here we gotta say vertices.len, so basically we're offsetting it by vertices.len. And yeah, used of moved value staging buffer. Make sure to clone this. And I guess let's see, borrow, oh, not here, here. Let's see, clone. I'm probably gonna need it here too, actually. Let's go. Clone, and there you go. Now let's see if this would actually work by any chance. So copy buffer, okay. Let's see, hold on a second, hold on. Why do we even have like multiple layouts here? What? This is crazy. I don't even know how this actually works. Oh, I see. Oh, shadowing. Oh my god. I don't even know how that worked before. Like, what? That's super weird. Anyways. Let's see. Yeah, I think that should be it. But we're probably gonna have some alignment problems. Let's just find out if this is gonna work. I don't think it would. Source slice length does not match destination slice length. Let's go. That's gonna be fun. Source destination slice length. What it was again? And where that happened? I guess here. Shouldn't probably using physical was 180. Okay. Source slice length, which is in this case this guy. Okay, vertices.len. Yeah, I guess what I'm gonna do, maybe, honestly, I think what I'm gonna do is create the buffers first, I think. So like, how do I do this? Yeah, we have the buffers, then the staging buffer. And let's see. So instead of std mem size of val, I guess what I'm gonna do, maybe just say vertex buffer dot size in bytes. Yeah, it gives us in bytes, and then maybe index buffer dot size here, and hopefully that would work. Let's see. And what else now? There you go. And here, cast slice vertices, I'm gonna say Oh, it was 180. I see. Okay, hold on, hold on. Go back, go back, go back. I know what's the problem here, kind of. Where is the thing? Yeah, and here, copy from slice. Now, this here, we're gonna say, let's see, we're gonna say 0, and we're gonna say vertices.len. Let's just say an experiment. Okay, and here maybe indices.len. Let's see. Console slice length does not match destination slice len. Interesting. Where? Here. So oh, what I'm doing here. I should get the length, like the size in bytes. So let's get the std mem size of val. Let's say vertices. Now, to be clear, this is not needed. This crazy stuff like this. I'm just experimenting. There's a much better solution in Vulkano. This is just me experimenting, which I'm actually going to show you in a second. I'm just trying to see if this would actually work out by any chance. Let's see. Size of val. Though I've done it before, but I don't remember how I've done it exactly. Anyways. So size of val indices, let's go. And let's see. Alright. Another error here. Alright. There you go. A lot of errors. Let's see what's up. Slice index starts at 72 but ends at 6. Oh, what? I see. I see. Now here we can have this like this. There you go, it doesn't work. Interesting. It worked so well. I don't know. I don't think this would work every time. I'm not sure if alignment would be correct, and I'm not sure what Vulkano helps me with too. So, but somehow this actually worked. I don't know. But basically, the problem was, first of all, I had the wrong thing here in the staging buffer where I was. Hold on. And also, what about index buffer though? I didn't bind it just yet. Maybe this wouldn't work. Let's see. Okay. Oh my god, it actually worked. Damn. Weird. But okay. I'll take it. That's very cool. But basically what I've done is but let's see, where is it? Come on, where is it? Yeah, here in the commands, then the copy commands, I had this wrong. I was passing length instead of size, but I need here size in bytes because I'm not using Vulkano's typed buffer here. I'm just using U8, basically bytes. I'm working with bytes here as to basically pack these two data into the same buffer. But one thing here though, I'm actually using the vertex buffer itself, the vertex buffer size itself, as to make sure at least it aligns with it in terms of size, though I'm not sure in terms of actual data if it would align well. But it seems to be working out anyways for some reason, though I'm not sure if it will work on all cases. But yeah. Though, what about, I'm gonna try what I had before, or honestly, this is fine. This is much better anyways. I'm not sure if the other way would have worked if I had the correct thing here. But yeah, this is one way of doing it, though I'm using one buffer, one staging buffer. Then I'm packing the data, like both the data in the same buffer. Then here I'm doing this shenanigans here. To do it. But yeah, I don't really recommend this way of doing it, but somehow it worked. I have no idea if this would actually work on all cases. But what I would honestly recommend instead is Vulkano's subbuffer allocator. So instead of this weird shenanigans here, we don't need this stuff, right? So I'm just gonna actually comment this out for a second. Though these of course wouldn't change, I believe, right? I think so, yeah. For the staging buffer right now, instead of this, I'm gonna go ahead. Now, I never used this honestly, but I've just read a bit about it in the documentation, and I think this is exactly what we needed. Though, let me see 1 second. There is a let's see. Yes, okay, so I have actually asked a question here. Hello, would it be good to use subbuffer allocator for staging data to device buffers? And Rua, one of the maintainers, said yes. So yeah, actually let's go ahead and try it. I never really tried it. Yeah, this one I'm gonna actually try in live. And in fact, even this one, I don't know. Like, it was much easier. I've done it somehow, but in a much easier way, but I can't remember how. But yeah, this actually works somehow anyways. So now let's just say subbuffer allocator equal to, is this live stream fine? Good. Live stream seems to be fine. Amazing. So now let's actually create a subbuffer allocator. How do you do it? There you go. I think this is the one. This is the one. And here we can create new or arrays from, oh, what? I don't think this is, oh, this is from palette, no. From stimulus, allocate size, allocates a subbuffer for sized data. Yeah, I see. Arena size, reserve. This takes self. Okay. new, and then you give it some create info. So let's give it memory allocator. Now this is basically the same thing that I've done before, but I'm going to be using this Vulkano abstraction to do it for me. It's like kind of like an arena allocator where it would reuse buffers, right? And I would recommend going this way because Vulkano would take care of the alignments and all that stupid stuff that could go wrong easily, and types and stuff, I think, but we'll see how it goes. So memory allocator clone create info, because honestly one of the things that really drove me away out of Vulkan is such things as alignment requirements and this and that and stuff like that. Bro, I just want to tell you, you know, copy the data here and yeah, take care of the requirements, take care of that stupid stuff for me. I don't care. But anyways, let's see subbuffer allocator create info. How are we gonna do this? It takes arena size, the initial size of an arena in bytes. Yeah, here we can give it a size because we already know what size they're gonna be. And the buffer usage, memory type filter. Lovely. Lovely. Let's go. That's what I'm talking about. And here we're gonna give it the arena size, which is gonna be, now we don't really need to give it this, but this is like, you know, vector reserve, like we're telling, because we know what the size would be at the end, so we're just telling it the size. And the size is basically, I believe, vertex buffer.size plus index buffer.size. And is this in bytes? I would guess so. Yeah, arena in bytes. I'm not sure if I should give it the actual data in bytes or the actual buffers in bytes, but I would guess buffers in bytes. But anyways, buffer usage. Here, buffer usage. And actually, let me see more about the documentation. If you need to allocate buffers of size, if your data is done, try and make an indicated guess. Anyways, buffer usage. Here, I want you to just be transfer src. And because I'm going to be using it for staging buffers. And next up is memory type filter. Now I honestly don't care too much about memory type filter, I guess, but what if I say default? Default, what the default is, let's see. No, I actually care. It should be preferred device, but the author should be something else. So, and by the way, let me actually ask in the Vulkan server, is it better like, which memory is better for staging buffers? Let's see. Thanks. Is it better to put staging buffers? Or is it better to use is it better to use device, prefer device, or prefer host for staging buffers? Let's see if they can actually answer me real quick. But basically I've asked in the server, is it better to use prefer device or prefer host for staging buffers? And let's go, if she's typing. Depends on what you're using it for. Let's go, I'm using it to stage, vertex, and index data. Let's see. So from host, yep. Let's see. All right. Then you want preferred device. Amazing. Next. Mark is also typing. Interesting. This is another. Like these are the main contributors and actually the maintainers, Mark and Rua. They're also pretty friendly. Please read the docs of memory type filter you both. What? I guess it's wrong. Maybe we should go with the prefer host. Interesting. Oh my god. Yeah, we need to read the documentation for sure. Let's go. Let's see. Memory type Vulkano. Why I'm getting Chinese or like Japanese for just searching for memory type filter Vulkano? What? Bruh. Let's go to Vulkano docs. And let's look for memory type filter. Memory type filter here. Let's go. And yeah, here you go. Describes what memory property flags are required, preferred, not preferred, and picking memory types. And there are they for staging. Okay, for staging, the resource is only ever written to sequentially. Also, since the device will only read the staging resources once, it would yield no benefit to place it in device local memory. In fact, it would be wasteful. Therefore, it's best to put it in host local memory. Let's go. All right, so prefer host. Yeah, that's what I was using it before, but yeah. Interesting. So the best for staging buffers is host local, essentially. So yeah. Right, thanks. Let's go. So it should be prefer host. Let's go. All right, hold on. What's going on here? Okay, just making sure this works. Okay, so we should use buffer usage transfer src, and for the memory type filter I would go with memory type filter. And actually, how to use the in the documentation, hold on. For staging, go with prefer host. Okay, so let's go with memory type filter, prefer host, and memory type filter host sequential write. And that's basically it. I think subbuffer allocator is never used. Subbuffer allocator. Okay, lovely. So we have created the allocator, or the arena allocator kind of thing. Now I guess we could allocate some subbuffers from it. So we could allocate a vertex staging buffer, I believe, from it. So, but in like here, it's probably gonna create one buffer for them both. But yeah, so subbuffer allocator to allocate, and here I can say allocate, I believe, size. Actually, allocate slice probably, maybe. Allocate size. What this does? Allocate subbuffer for size data. Subbuffer T or slice. So I actually have multiple data, so I probably should go with allocate slice. And here I should go with the len. Well, the length would be vertices.len, right? And add save cast to device size and allocate slice. And by the way, Mark is probably the one that actually creates the allocators in Vulkano, I believe, but I'm not sure. So that's why he told us it's probably the one that created the documentation for that one, for this one, and maybe even this one too. But anyways, vertex staging buffer, it's pretty interesting. Allocate slice. Great. And here we're gonna go with vertex, I believe. Vertex. Yeah, basically. So here we're telling it the type of the subbuffer, and here we're telling it how much vertices. That's it. Now the index staging buffer, and I believe this would be much more efficient than creating a single buffer for every single one of them. Here it's probably gonna reuse one buffer. Here it's just giving me a sub buffer. You know, it's kind of just like a slice, just like I was doing here manually. But this is very error prone, and I'm probably not taking into account alignment, so it's probably wouldn't work. But I was lucky enough that it somehow worked, I guess, but I'm not sure. Anyways, so here this should be U16, and here we're gonna say indices.len. So yeah, honestly, they probably should say maybe from iter or something like that. They should add that maybe. I may try to contribute to Vulkano later on. Anyways, vertex staging buffer, index staging buffer, and now we gotta write the data, right? So how are we gonna do that? And by the way, actually, buffer from iter, what it does return, like, hold on. So you give it a memory allocator. Oh no. What about subbuffer allocator then? Does it have such a function? Let's see. New from, let me check the documentation here. So let's go to subbuffer allocate. Great. And let's check this up. So for example, here subbuffer allocator, each loop allocates a new subbuffer, allocate sized in wrap, blah blah blah, update buffer, arena size, reserve, allocate size, allocate slice, allocate in size. Yeah, there's no from iter function, so we just gotta do it manually. I think you just allocate a subbuffer. Then it seems you dereference the subbuffer, then you say .write .enwrap equal to the data. Interesting. Okay, let's try that out. I think so. Subbuffer allocator. What I'm doing? No, we're gonna say vertex staging buffer. Well, I gotta dereference it for some reason, and then I gotta say .write and then this equal to vertices data, I believe. The size for values of type vertex cannot be known at compile time. What do you mean? Well, can you just get this and see it, writer? .write. Oh, that's interesting. Let's actually remove this and see what's up with this. Okay, I guess this is what I need in my case actually. And here I'm gonna say, I guess I could possibly do this, something like that. Like if I say writer dot, let's see what we have. Take contains a line to, like if I say vertices equal to vertices, what's gonna happen here? Cannot assign a new value to an immutable variable. Interesting. What if I do this? No. Very weird. Maybe copy from slice and then vertices, and then possibly like this, maybe. Maybe there's probably a better way, but I'm not sure how to do it. Anyways, so that's basically it for the vertex writer, or yeah, writer, vertex writer. Let's go with that, and then let's also get basically the same thing but for indices, I believe. And let's see, so indices writer, Okay, copy from slice indices. Let's go. But yeah, let's go. So indices, but found expected. Oh, index staging buffer. Let's go. And I think this should work. This should work fine enough, I believe. And Vulkano would probably take care of alignment here for me, so I wouldn't care about that. Cannot find value staging buffer in this scope. Yeah, so this should be vertex stage buffer. Now we don't need all this slice stuff here right now. So let's go with vertex staging buffer, and here let's go with index staging buffer. Let's go, and yeah, I believe that's probably it. Alright, we got our beautiful triangle, but right now with staging buffer allocator, so I think we're probably only using one buffer for staging, which is amazing. But right now, I'm surely, like, I know for sure that Vulkano would do the right job here. I don't need to care about alignment and stuff, so this should do the trick. And this is actually the way that I would recommend to do it. This is basically, this sub-buffer allocator is just doing what I've done manually right now that I've shown you. Now I don't need any of this weird crazy stuff and manipulating bytes, and like you can, even if you're experienced, you could either, like, you can get that wrong very easily. So yeah, even if you're experienced. And actually this should be sub-buffer. There you go. Okay, amazing. And yeah, that's it for buffers. That's super amazing. Now what's next? I don't know what to show next, honestly. I'd like to show how to like actually load data from like an OBJ or GLTF and stuff like that, but I don't think I want to do that in this video, like in this live. Maybe the next one possibly, but I think let's see, hold on, let me see 1 second. What do you guys think? What should I do now? I think maybe I'd like to add MSAA, multi-sampling, possibly. Because if you see here, the geometry is pretty rough because there's no multi-sampling happening. So as you can see, it's pretty jagged. And actually, this is a good time to show you another cool tool, which is called RenderDoc. And this is really helpful. Let me show you one thing here. So let's get our debug executable here. Where is it? Vulkanox or yeah, it's 200 megabytes because it's debug build. So don't panic. Copy location. And let's go to launch application. Executable path, Vulkanox. Let's make sure that it's in the right working directory. I don't think it matters currently because we're not loading any files, but anyway, launch, and there you go. Right now we're running. Now it's in VSync and my monitor is 75 hertz. So yeah, there you go. And yeah, now let's get a capture. I could capture PRT screen or F12, I believe. So I'm gonna go with PRT screen, and there you go. I have captured the frame now. Now it loads this image for me, and there you go. Now I can see my output here, and I can see what it's all doing basically. So that's pretty cool. And as you can see, it's pretty jagged. Look at that. You can see the individual pixels, and it really looks so rough on the geometry. pretty much. So I want to fix this, and we can fix, like, there's a lot of solutions, but the easy, like the straightforward solution is to use Vulkan MSAA, which I think it's multi-sampling. It's to be exact, I think it's super sampling, possibly. I'm not sure, honestly. Anyway, the other thing that I want to show you here, I want to see if how much buffers we have though. Well, at this point we have two buffers, the vertex buffer and index buffer, but I want to see before that, is that possible using render doc? I'm not sure if it is actually, but actually the sub buffer allocator, when does it drop its buffers? I think it drops it when it goes out of scope, or I guess, oh, actually when the sub buffer, I think when it gets out of scope, right? I see. Well, that's interesting. I really want to see how much buffers it makes. I guess we could try to find out somehow. So like we could say, now after allocating this stuff, maybe we could try to find out how much buffers we have. So let's see, print, well, info, or let's say subbuffer allocator. What is going on wrong with this guy? What? This is super stupid. Okay, I don't know what happened there. Okay, so we have arena size, allocate size. How do I know how much allocations there is? Like how much buffers it's using. I'm not sure if it's even possible. Reserves, the arena size. This gives us the current size of the arenas. Is it in bytes or what? I would guess in bytes, so this is probably not what I really want. Reserve, allocate size, allocate. Yeah, let's try this and see, but it's probably not gonna be what I want, really. It's probably gonna be the actual bytes that are allocated. But anyway, never mind. But it's probably only making one buffer, really, because it's supposed to. But anyways, so now what to do next? Should I go with that or no? We could also check the VS and TCS, and there's a lot of stuff here actually. Vertex input, mesh view. Oh, what's happening here? Are we in the right place? Hold on. If we go back to texture view, what is this? This is the read and write. Okay, can I check out the pipeline state now? There you go. You can see the mesh. Let's go. Amazing. And you could do all sorts of cool stuff actually. And this is like the VS out. Now this is the VS in, the vertex input, and this is the vertex output. And for some reason, interesting. Oh, yeah, this is what comes in, and this is what comes out. And here it's showing the actual swap chain, I guess, like the bounds here. And this just seems to the bounding of the actual data itself, I guess. Yeah, that's pretty cool. And what else? I wanted to show pipeline state, and as you can see, it's using triangle list because that's what we have chosen, and it's using this buffer, and this buffer have a position and a color attribute. Let's go. And with the offset, this and that, which is pretty cool. TCS, TS. The rasterizer, this is what we're using for the pipeline. Great, this is the scissor and the viewport. And then there is FS, FB. This is, what is that? Frame buffer. So we got swap chain image. This is our frame buffer that we're rendering to. This is our color. This is the attachment I was talking about. There you go. Pretty cool stuff. And compute, I guess this is, or what? CS. I don't remember what's this, but anyways. No, I don't think compute. Not sure. Anyway, what else? Let's see. There's also the resource inspector, as I said, which you can check like all the resources that you have. For example, we have one command buffer, I think. We have two buffers. We have a command pool, one command pool. We have, one descriptor layout device. We have all these fences for some reason, because Vulkano handles them, manages them. So, and we have graphics pipeline, image view, instance, memory, blah blah blah, whatever. And we have 3 swap chain images. Statistics. Here you get the statistics. We got the draw call, 1 draw call, dispatch call 0. We're not doing any compute, at least not yet. API calls 20 API calls, and API draw dispatch call ratio 20. And API calls 20. Okay, 3 textures. Interesting. 3 RTs. Not sure what's that. Render something. I don't know. 5.49 megabytes in average texture dimensions, 0x0. 2 buffers. What do you mean by 0 megabyte? Total what? And 5.49 megabytes. Grand total GPU buffer plus texture load. Not sure what's seen for the buffer 0 megabyte. What? That's weird. Anyway, so that's, I believe, pretty much what I wanted to show for a render doc. And you can see here the commands that's getting done. And like when you begin rendering, as you can see, for example, it just clears the screen. Then when you call vkcmd draw, it actually draws the triangle. Okay, pretty cool. Pretty cool. Lovely. Yeah, swap chain image. I could see the device, the swap chain, the image view, and the resource initialization parameters. I could see the stuff that we initialized the swap chain with, for example, here. The swap chain image with. Yeah, that's pretty cool, actually. Lovely. So yeah, and here you got like a timeline of the frame. Like, this is where you submit and where the capturing started. And here we have actually, yeah, here where we actually start executing stuff. Here we got the color pass, where it's begin rendering color or begin rendering, and then vkcmd draw, and then vkcmd end rendering, and here vkq submit, end command buffer, here where we ended the command, and here q present. But anyway, so I think that's all I wanted to show, really. Window, texture viewer, pipeline state, API inspector, timeline. Yeah, I think we have seen most of this stuff. You could see the API here, what's happening basically, but yeah. And here the call stack, I guess. Anyway, yeah, that's pretty much it. So right now what I want to show you, either multi-sampling, or actually let me show you some other things before multi-sampling. Let me show you, for example, let me make sure the stream is fine. Yeah. Oh, I forgot to do the camera. Oh my god. Okay, anyway, whatever, doesn't matter. And what else? Main.rs. Okay, what else I wanted to show you? Let's see. For example, let's show you instancing. If we can, I'm not sure, but let's see. Vulkan renderer. Where is it? Let's see. Where we're doing the draw function. There you go. Okay. So notice here that we also have instance count. So if we can actually do whatever we want here. We can write whatever we want. But let's see if this would work. Yeah, this actually works. but you don't see any difference. Why? Because we're actually drawing 3 triangles right now, not just one, but all of them are in the same spot. You know, they're in the same position. So how we could change that? Well, we gotta change the the thing, like how do we transform some vertex data depending on some parameter? And in this case, the parameter is the instance ID, or yeah, basically something like instance index, sorry. But anyways, so let's go back to the shaders, okay? Let's go to the vertex shader, because it is the one that takes the vertex input and then transform it into vertex output. Here currently we're not doing any kind of transformations, we're just outputting the position as it is, basically. So how are we gonna do this? Well, let's see. Like we could say, for example, plus vec3, because the position is vector 3. And we could say, for example, maybe let's shift it a bit in the x-axis, possibly like 0. Let's say 0.1 or something. I'm not sure if you can notice that offset. Let's see. But basically this would move the triangle a bit to the right, I believe. 0.5. Let's see that. Well, the coordinate system I think goes from -1 to 1, or is it minus? Yeah, from -1 to 1. As you can see right now, the triangle got offsetted in the x-axis. And we could do the same with the y-axis, z-axis, etc. We could also go ahead and say times to scale the triangle, you know. So here, let's say, for example, we want to scale the triangle up 2 times in the x-axis. So, oh my god, we're not going to draw any triangle at this. We're going to draw a triangle, but it's not going to be visible. Because, you know, I have 0 here. It should be 1. Because I'm not offsetting anymore. This is multiplication, and the identity of multiplication is 1.0. So let's go. Addition have an identity of 0. So, and there you go. It got stretched in the x-axis 2 times the data that we got. But yeah, this is just a little thing right there. But here, let's say I want to actually offset the triangle depending on which instance I'm drawing, because currently I'm drawing 3 triangles, 3 instances of the same triangle, but they're in the same position. So how can I do this? Well, there is vec. We could offset it by, let's say, let's offset it by GL. I believe, if I don't remember exactly what it's called, but I think GL vertex ID or index or something like that. Oh yeah, there you go. Did you mean GL vertex? Lovely. That's what I'm talking about. And there you go. But the thing is, this would be 1, like 0, 1, or 2, or stuff like that. And let's scale this down a bit. Let's say maybe 0.1, or let's see 0.1. Okay, because otherwise this would probably go out of the screen, because it's 1, 2, 3, blah blah blah. And let's see, this is weird. This is not what I expected for some reason. I guess I forgot something. Instance count 3. Yeah, so what's happening? Let's say 10 instances. I'm not sure what's happening here. Something is weird. Yeah, I probably missed something. Well, let me make sure that this is a float, I guess. What? Weird. This should work just fine. I don't know. But anyway, this should have worked in theory, but I'm probably missing out on something. So for now, let's leave this until later, actually. But generally, what should have happened, if it worked, it would have had like triangles like this. Like every triangle instance would get offsetted. But I'm not sure what's wrong here, and I don't want to spend too much time on this, I guess. So, oh, hold on. Let me just make sure that the other things is 0, just to make sure nothing weird is happening there. But, interesting, no. I don't know, I'm probably missing something here. So anyways, let's just go to the other thing that we want to do. So now let's just remove this. Oh. This shouldn't be vertex, this should be instance. I don't know how I missed that. Let's see if this works. There you go, that's what I'm talking about. Oh my god. Let's go. So right now we got multiple instances of our triangle. And notice that it's actually offsetted by that amount. Like by 0.1 every instance. Like instance 0 would resolve to GL instance index would be 0, which means it wouldn't get offsetted. But when this becomes 1, which is the second instance, it would be 1 times 0.1, which means 0.1 offset in the x-axis, and so on and on, which is pretty cool, huh? Lovely. Let's just say actually this, so it would do the job in x, y, and z, and it would right now go diagonally. So there you go, pretty cool. So this is 10 instances of the triangle, basically offsetted. Let's say we also not just want to offset it, but also to scale it. So what we could do then is times vic3 gl instance index, and let's say I don't want to scale it by 1. Let's just say 0.1. Actually, like that's okay. So every triangle would be 0.1 times scaled. Okay, there you go. That's weird. Okay, so the first triangle is actually not shown because it's 0. This would resolve to 0, so it would be just 0. So that shouldn't really happen, honestly. Let's say +1 here. So it would skip that part where it would be 0. Yeah, and the first triangle right now, there you go. And now it, like every second instance would become basically bigger. So like I could make this more clear by doing this. Oh my god, no. this didn't work. Well, it worked, but it's too big, right? So yeah, anyways, let's just go back to 0.2 for example. And notice here we have offsetted the GL instance index by 1 in the shader, but we could do it in another way. Look at that, it's bigger every time, but we could do it in another way. Instead of offsetting it in the shader, we could also just offset it in Instead, we could offset it here in the first instance, for example. So we would skip the first instance, but we would only draw 9 instances now. But yeah. There you go. So this also works the same way as before. But right now, instead of offsetting it in the shader, we're offsetting it here. But actually, it's less than, like before it was 10 instances, but right now it's just 9. So if you wanna to like the shader before, it would be 11 here. But anyways, so that's just, I wanted to show you this before we go further. So instance count 1. And now let me just remove that new shader code for now. So we don't need this anymore. Let's just keep it as it was. Lovely. The other thing that we could actually do right now is animation. But to do animation, we need to transform, let's say, the vertices or the fragments or the colors somehow. Now we could transform it in the CPU, then stage the vertices, like stage the data again, but that's super bad. Like doing that every frame. I mean, unless of course you actually really need that, but you could easily do this in the shader. But the thing is, you need something that changes from frame to frame. What is that something? So the actual output would change. Otherwise, nothing would change. So there is 2 things that you could pass in that changes from frame to frame. For example, there is either the frame count, like the frame, like which frame you are in. Let's say frame number, like is it frame 0, frame 1, frame 2, or frame 3. But this is bad because, well, what happens if you're running at 10,000 frames per second instead of 1 frame per second or something like that? It's gonna be different. So it's not like frame rate independent. So the best way to actually do animation is passing time and using that as a variable, because that changes every frame. And yeah, so how we could do this? Well, again, just like everything else, there's a lot of ways to do this. We could use uniforms, or we could use push constants, and there's probably a lot of other ways maybe to do it. But I think for time, at least for now, I think the easiest best way maybe to use push constants. Though I don't remember how to use push constants in Vulkano, so I gotta check out one example there. And yeah, let's try to pass in the time to our shader right now. Now you could also make a uniform buffer and pass the time through it, but like the time. Now push constants is actually ideal for per draw call, like per draw call changes. Like if you're gonna, like when I say draw call, I'm talking about the draw function here. Where is that? I'm talking about this guy. Hold on. Yeah, I'm talking about this guy because in fact I don't have to like just go with one draw call. I could go with second draw call, let's say, and maybe change change one of these parameters, right? But yeah, or I could draw something else, but of course I gotta bind some other vertex buffer before that and stuff like that. But whatever. Now let's say I want to change some data in the shader after every single draw call, then the best thing would be to use push constants for that. So yeah, like here you would change the push constant to something, and then here you would change the push constant again to something, and so on and on. This is what it's intended for, because you can only have just a little bit of push constants. And in fact, in mobile phones, for example, it is actually bad to use push constants because a lot of them just simulates push constants kind of. So but in desktop, push constants are pretty fast, but still you still have just a limited size of push constant that you could use. So you gotta use it just for things that you really need to use it for. Time would probably be better sent maybe through a uniform buffer, since it's not really changing per draw call, it's actually changing per frame. But for now, we're just gonna use push constants, okay? Just to keep it simple, I think. And yeah, also it depends, right? So anyways, let's go right now to, I'm gonna look into the push constants example, because I don't really remember how Vulkano does it. Let's see, long time. Okay, so first of all, we gotta change our shader. And here, where's the shader? There you go. Okay, in our shader, we could pass in some push constants into the shader. Okay, so here, frag color, and then here I could say this. So layout, push constant, uniform, push constant data, and then here you call it whatever. In this case, they call it PC, which stands for push constant. And here I could pass in the data that I want. In my case, I'm only gonna have one thing, which is the time currently. So we're gonna have float time. Hold on, yeah, float time, like this, right? And then here I could say, let's use, sorry, the push constants. Let's say, for example, sine times sine of time. And there you go. So this is our little shader. Great. Now, how do we pass the push constants from the CPU? Well, we have some other steps to do. Let's see. Pipeline, CSI, whatever. Okay, let me see where they're doing that stuff. Okay, CS push constant. Oh, interesting. So they're doing the reflection for us. That is lovely. Vulkano rocks. Let's go. So you basically do it something like this. So the Vulkano shaders macro basically also generate the push constants struct, which is honestly very amazing. But anyways, so here what we can do is CS push constant data. I think we gotta make sure that it's public though, so we can access it from the renderer. So pub vs, and then here in the Vulkano renderer, or the Vulkan renderer, we're gonna go to probably just before the command buffer. So begin. Okay, so maybe somewhere around here, possibly. And here we could say vs, but we gotta import it, of course, because it's in the other file. And missing field in push constant data initializer time. Let's go. You say time. So as you can see, basically here Vulkano shaders actually did the reflection for us, and it gives us even an the struct directly. So right now we can just fill it. We don't have to care about layout and all sorts of weird stuff. So here we could pass in, yeah, we need to keep track of the, yeah, I see. So here's what we're gonna do. We're gonna say self dot, well, std time instant now minus let's say self dot what I want to call it. I don't know what to call this. Maybe start time. Let's go. And right now we gotta actually initialize that and add it. So let's call this start time. This is gonna be an instant. And then in the initialization we can add it. And we're gonna just say, gonna initialize this to into std time instant now. So of course this would just be initialized at the start of our render. And then here we could pass in instant now minus self.start time. But of course this gives us a duration, so we should convert it into something. And in my case, I'm going to convert it into seconds. So as seconds f32, right? And this should do the job. But I guess maybe we still have to, yeah, we still have some other step, which is, yeah, we gotta actually set the push constants before the draw call. Or yeah, basically. So like the draw function here, before it, we could say dot push constants. And here we gotta give it the pipeline layout. Interesting. Do we gotta change something about the pipeline layout? Hold on a second. Let me make sure that is. Yeah, probably. I guess, maybe, not sure. But let's see. Let's just give it the pipeline layout that we have anyways. And we can see later what's happening there. Where is the layout though? Oh, we don't have it here. That's interesting. Because we gotta... Hold on, let me see if something have changed in the pipeline layout. No, it's probably, even if there is, it's, yeah, you gotta change the pipeline layout, but we don't have to, because we're using that into pipeline layout create info from the stages, so it's getting done for us, like it's automatically done for us through Vulkano, through the shader itself, so it's automatic basically. So right now what we gotta do is basically just make sure that we actually store, well, we don't have to actually, yeah, we already have access to the pipeline, right? Vulkan device pipeline. Yeah, graphics pipeline. And then we could, from that, we could access the layout. There you go. Amazing. Vulkano is just amazing. Let's go. Arc pipeline layout, but found arc pipeline layout. Let's go. Let's clone this, and yeah. As you can see, Vulkano really like lets me do the actual thing that I want to do instead of caring about stupid Vulkan requirements and stupid stuff like that. But anyways, offset 0. What offset? What is offset? I forgot. It's gotta be 0 here, I believe, but let's see. Yeah, it's 0. I'm not sure what is offset though, but anyways. Or maybe it's not relevant to us since we're using Vulkano reflection or something. Anyways, now let's actually try this out. And it should work if we're not missing anything. So let's go. And there you go. We're using push constants to actually pass the time every frame to the shader, and then the shader, what it does, it takes the sign of that time value, because time could be like very big, but sign always goes from -1 to 1, you know. So we're passing it to the sign function, and this is what we get. So like the time is kind of like the offset in that sign function. And yeah, right now it's basically, look at that, it's going from -1 to 1. That's why the triangle gets flipped to the other direction. Yeah. Do we have calling on? I think we do, but just I'm gonna make sure. Yeah, I do think so, but let me just make sure that's the case actually. Yeah, where do we create the pipeline? Let's see. Let me make sure we have calling on though. Otherwise we're going to be drawing two triangles even though the triangle is not visible, which is not ideal. So let's see where that's the case. Input assembly or what? I don't remember where it is. This is not this, no. Rasterization. Yeah, here it's in call mode, and the call mode default is none. Okay. So here I gotta actually change something. I don't want none. Otherwise it would be like drawing the triangle that the actual user sees and also the other triangle in the other direction, which the user doesn't see. That's why in a game, for example, if you enter into a mesh, you're gonna see nothing because the inside triangles of that mesh doesn't get drawn because of calling here. And calling is like, how do you actually determine the direction of the vertices is through let's see, yeah, through the index order. Like, how do you define your vertices? Is it clockwise or anti-clockwise? Now, depending on your rasterization state, what kind of did you choose clockwise or anti-clockwise? You gotta define the indices in that direction so it would show up. But anyways, so rasterization state. Let's see how we could create this. Rasterization. Here we're just gonna go with the default values. I do remember by default it's counterclockwise, which is what I want, but let me just make sure. Front face. Yes, it is counterclockwise, so that's good. I recommend counterclockwise. And what else? Yeah, I want to change the call mode because yeah, I think it's default, so it's conservative. Otherwise, if you have done the wrong order, it wouldn't show the triangle at all. And who knows, we may have some problem like that here. So call mode. Call mode. We want to call the back face, so we don't want to show the back face. We don't want to draw it. And yeah, let's make sure our vertices order is correct though. Otherwise, it wouldn't show any vertices at all. There you go. It seems to be correct. There you go. So yeah, it's correct. Nice. Otherwise, you gotta flip the order of the vertices. Or the indices, sorry. How are you doing? Read one. Welcome to the live stream. Yo, it's been a while. Yeah, it's been a while. How is it going? I'm having some fun here with Vulkano. Best fun I had with Vulkan so far. Let's go. And right now we could actually have, let's compose it all together. Actually, let's compose it all together. Let's say we want 10 instances, and let's say we want a lot of windows. How much windows here? Let's say where's the windows? There you go. Let's say 4 windows. Actually, let's just say 3 here because these are the secondary windows. And the primary one would be the 4th. And what else? Yeah, so now we just gotta change the, what is it called? The Vulkan device or what? Yeah, let's go to the shader and let's change this. And let's say plus, for example, vec3, and let's just say plus vec3. Let me see what I want to do with this. Hold on. Plus vec3, and I'd say, I guess, gl vertex, instance index, and probably times 0.2 or something. And what else? Yeah, let's see what this would produce. So we should have 10 instances and 4 windows. Look at that. Oh my god, what's happening? Hold on. Yeah, it doesn't. Anyway, let's just do this. There you go. I don't know why it's not aligned well. There you go. Let's go. And there you go. We have 4 windows with 4 renderers with 10 instances of the triangle, where the triangle is just like going up and down. That's pretty cool. Let's go. So yeah, I really don't know why it doesn't want to close the window, but anyways, let's try something else. Maybe here plus vic3 gl instance index times 0.2. And let's maybe say here plus sign of pc.time or something. Yeah, just random stuff. Just showing you what is possible, kind of. Although a lot more stuff is possible, but yeah. Yeah, okay. Is never read. Weird stuff is happening. But one thing that is not pretty cool about this is that every window does have the same stuff rendered to it. Nah, that's super boring. Let's change what is being happening depending on the window. So how we could do that? Well, what is the thing that changes from one window to the other that we could use it as a variable in our shader to change the rendering depending on the window? Which is, let's say, a window index. Like if it's 0, or is it 1, or is it 2, or is it 3. So let's pass in, instead of time, just like as time, let's pass in, let's say, the window ID or the window index. So let's say uint, or is it what? Unsigned int. Yeah, I've used a lot of languages. It's becoming weird. Anyways, so let's say maybe unsigned int window ID. I'm not sure if I gotta care about in alignment in this case, or maybe Vulkano is doing that stuff for me, but unsigned int window ID or window index. Unsigned reserved word. Ooh. How do you do unsigned int in GLSL? I guess uint like this, maybe. And let's go. So yeah, uint window index. And I don't know, let's say, I think uint, yeah, would work, right? It does compile. I mean, Vulkano basically shows me if there's any error. It compiles at compile time basically and shows me if there's an error here. So yeah, that's pretty cool. Now window index, great. Now what we gotta use it for in the shader? Well, we could use it for all sorts of things, but I guess let me show you some colors right now. Some changing colors maybe. Yeah, so right now, until now, I only shown you vertex transformations. Let's show you some fragment transformations. And for that, well, we're already passing the frag color from the vertex shader, so I guess let's play with that a bit. Let's say, I don't know. Sadly, we don't have, I guess, hue and stuff like that in GLSL, isn't it? Hold on, GLSL hue shift function. Is there something like that in GLSL? There's yeah. I don't think there is, but let's see if I can find something about that. Yeah, I gotta do the math. I don't want to do the math. No, there's no built-in function basically for that. So are you using C-line for C++ projects? No, I'm using Rust Rover. I would have used C-line before because Rust Rover didn't exist, but right now JetBrains have just released a dedicated IDE for Rust, which they called Rust Rover, and it's still in preview mode. Though JetBrains products are of course paid, but Rust Rover right now, since it's still in preview mode, so it's free currently. So if you want to try it out, you better try it out from now, before it leaves preview mode and becomes paid. So you have to get a license to use it then. But anyways, so color. I'm not sure what I want to do here. Let's say times. I mean, I also gotta pass actually the window. Yeah, I also gotta pass the window size if I want to do something here. Now I could either pass in the window index, or I could just pass a float. Does it support C, C++ as well, or just Rust? Rust Rover, I think only Rust, but it could also be C++ and stuff, but I'm not sure. But C-Line actually does. And in fact, they also have a new IDE called C-Line Nova that would replace C-Line, basically. And C-Line Nova is also in preview mode, so you could also try that out too, for free. So, but anyway. So here we could either pass in the window count, I guess, or otherwise we could just say, or we could just pass in like window. But yeah, let's pass in the window count too, I guess, maybe. I will give it a try, thanks. All right, you're welcome. So color, let's say for example, color times window index, maybe divided by window count. But I gotta make sure to cast this though into float, otherwise it wouldn't work. It would work, but an unexpected right parentheses. How do you actually cast stuff in GLSL? What? I guess maybe like this then. Maybe. Is that how we do in GLSL? I guess, seems like. I actually gotta cast one of them. Okay, I think this should do the trick. Though like for this specific use case, I could have just used like a float and call it window normalized index or something like that. But anyway, let's just pass these two, why not? And for that, let's see how we can do this. I don't need to change anything here, I believe. Probably. Color blend state. Yeah, like Vulkano would do that for me automatically, I think. But what I gotta change is in the renderer where I'm passing the PS or the PC. Notice that right now it's telling me that there's missing fields because Vulkano did the job for me. And now I could just pass in the window index here. But I gotta keep track of the actual window index that we are doing, or should I say the renderer index, but yeah. So how am I gonna do that? Well, I guess let's say self.window_id or something, or let's say maybe self.id, and then I mean, I'm probably gonna revert this. I don't really need this stuff, but just to show you some example. Basically, for now, let's just hard code this window count, honestly. But we could have done it otherwise. Here, I don't have any other choice than just to pass it, basically, for now. So, yeah. But yeah, you know what? Let's just say window count. I'm gonna remove it later on, but anyway. Just say window index here, and then here we're gonna have like window index u32, let's say window count also u32 or something like that. We could have also done it with usize actually. Yeah, let's go to usize. Well, this gotta be like this actually in Rust. But then I gotta actually give it that. So I gotta get it here. So window index usize, comma window count usize, and then I gotta pass it in. And here show missing fields, and I gotta fix something. I gotta cast this as u32, and no field window index, and finally window count as u32, and then we can pass these from the app, I believe. Yeah, from the app, and here where I'm creating the Vulkan renderer, I could provide the arguments. Yeah, I need to pass in here the window ID. Let me just pass it whichever for now, so it formats my code here. Okay. Now here I need to pass it the window index, which is we actually have it already, which is amazing, and the window size. Okay, so let's get the windows len. And yeah, that's basically it. Though I gotta change it here too. I gotta actually make this into a function. But anyway, I'm excited. So how are we gonna get, yeah, self windows.len, and there you go. This should actually work. They should actually work now. And this should basically change the color depending on the window, where the first window would probably be black, and the last window would probably be the most vibrant, I think. Yeah. Look at that. There you go. Because I'm basically multiplying by the window index divided by the window count. So like the first window would have just 0 multiplication by the color, and then the last window would have 1, and the other ones would in the middle would just be interpolated. But yeah, that's just a little example, but you could do all sorts of weird stuff. I think honestly it would be much nicer to change the vertices. It would be cooler, I guess. Let's go ahead and do that. Vulkan device, and let's change it here. Okay, so instead of the color, I'm just gonna say I have a lot of weird stuff here. Let's say plus cosine, whatever. This is just random stuff. And float window index. Yeah, honestly, I don't need the window count here. Fine. Like you could pass to the cosine sign, whatever. It would just work, I think. Okay, so now it would change the position depending on the window, because it's a variable there that we have included. And yeah, let's see what happened. Weird. No, this is not great. Hold on. Plus cosine. Let's actually say Mm. Let's grab this guy. Let's remove it from here. Let's maybe sign off window index. I guess sign off. Yeah, this would change the scale depending on the window. I gotta offset it though. Yeah, so now the scale of the triangles would depend on the window ID. Here, the first window is 0, pretty much. And yeah, but you got the point. I think you got the point here. Just by doing all this stuff, you could pass all sorts of things. For example, you could pass the mouse position, let's say, and all sorts of weird stuff. But for now, honestly, let me just remove this window index. Maybe let's try to pass in the window, the mouse position, for example. This is gonna be the last example of this. Yeah, okay, let's try. Vic2 mouse position. And at this point, yeah, let's make this simple. Let's remove the, honestly, I'm gonna keep the time. I want it later on. And let's say position here. Yeah, I'm gonna need this here. What else? Okay. Now let's say plus mouse position. Hold on. Should we pass the mouse position as floats or as integers? I guess I'm just gonna pass in a normalized mouse position, so floats. But you could do whichever you want, depends on your use case. Here, so yeah. But I think what I'm gonna do is plus vic3 here 0 in the z axis maybe, and let's say mouse position dot x, for example, and mouse position dot y here, just as an example. Really, I'm just trying to show you some ways to do this. But yeah, selection out of range, in the card, yeah, PC, and there you go. Nice. Now we gotta change the other stuff now. And let's see. So we don't want to pass this anymore. We still have the time, but right now we gotta pass in the mouse position. And the question is right now, how do I get the mouse position? Interesting. I gotta get it from winit, but the problem is I don't think we have access to winit here from the Vulkan renderer. Yeah. But well, I guess we could do something pretty quick here and say something like self.mouse position. Right, and this would actually be a vector 2. Add field. Oops, hold on. Let's call this mouse position like this. Oh, OBS disconnected. Now it's back, I think. Yeah, back into business. Let's go. Alright, so what we got here, let's try to create this, I believe. Align fields in a single line. What? But what I have created here. Oh, it didn't give it any time for some reason. Weird. But I guess if 32 2, is it the opposite way? No, it's fine. Seems like. Oh, expected padded if. Oh yeah, Vulkano does the padding for us, like the alignment. which is interesting. Padded F32. Oh, okay. That is amazing. So yeah, this is where alignment kicks in. Vulkano actually does that for us. But we still have to give it like... Can we say maybe the into here? Not sure how Vulkano... Ooh, okay, so I guess that's what padded is for. So you could... Oh my god, this is nice. Amazing, love this. Okay. Because basically structs that you pass into the shaders gotta be aligned. I think to 16 bytes, I believe. I don't remember, which is basically like VIC4 kind of. But yeah, anyways, so right here Vulkan just handles that for us by using that padded type, and then you could, I guess, just use into. At least that's what I think it would be. And now how are we gonna do this? Well. Now we don't know what is the mouse position at this point, so I'm just gonna add here, and I'm just gonna set it by default as 0, 0, I think, for now. So 0, 0.0, 0.0 by default at the initialization. But then let's say in the app where I have access to the actual events, I could say window event mouse input, and this actually probably gives us some stuff. I never really used this mouse input. I think it gives us the device ID, so which mouse, so we could actually handle, I guess, multiple mouses. Yeah, element state, and the button. What is the element state though? Yeah, is it pressed or released? Okay. Okay. And the button that got pressed. But no, this is not the one that I want. I want the mouse moved input, and I think mouse. I guess you cannot maybe do it here. Oh, cursor moved. I guess this is probably what we want. Cursor moved, and then what's happening here? Expected. Let's see. Position, physical position. Okay, it gives us the position and the ID. Now I only care about the position, so I'm gonna say this and this. And then what I could do is self.vulkan renders. Yeah, window ID dot borrow mute, because it's a ref cell inside an arc, and then we gotta go ahead and let's say update mouse mode position. Like really, the renderer doesn't have to do anything with the mouse position, but for our example we need it. So yeah. So what's up with this? Oh, like this. And now we gotta actually create this function because it doesn't exist just yet. So let's go to the renderer and fn update mouse position, or actually should be on mouse position moved or something like that. But anyway, whatever, who cares? So no method. Yeah, let's actually call it on mouse moved, for example. And then we're gonna pass it the position. Now mouse moved, and this would take the mouse position, and now we got the position from the app, I think. What's up with this? Oh yeah, we need to get the self. mutable self. Oh, what I'm doing, mutable self like this. Yeah, it's private. Okay, let's make it public. And finally, let's actually update the position. So self.mouse position is equal to, but this is an f32. I want to actually go ahead and basically normalize this guy. So what I'm gonna do, I can get the window size, right? Window, right? Dot inner size, and I could say position divided by self.window inner size, but I gotta make sure that they are in floating points. So how to do that? Interesting. Can I say maybe as physical size f32? What about maybe dot into? But no, let's just do it this way. Let's just do it this way. Position dot x. Oh yeah, you should do it like this, I believe. As f32 position 1 as f32 maybe. Yeah, what it's actually called? What? Oh, I see. So this should be physical position u32. And now here we could say dot x as f32, and here dot y as f32. And let's go. So now if we, expected physical position u32 found f64. Oh, it's floating point already. Okay, interesting. f64, amazing. So I do still need that, right? And yeah, but I also want to normalize this, so divide it by window size, self.window inner size, .window inner size .x, dot width, though let's get the size here. And as f32 divide by size dot height as f32. Basically we're gonna get a value between 0 and 1 because we're dividing the position in the window, the mouse position in the window, by the size of the window. So we're normalizing it basically, which means we're making it go from 0 to 1, range 0 to 1, instead of 0 to whatever size of the window. But yeah, so I think this may work. And let's see if I'm missing something. Let's see. And there you go, look at that. All right. This is pretty beautiful. Oh my god. Let's go. Look at that. Let's go. Nice. I'm having a lot of fun here. So yeah, pretty cool. All right. And we could, let's say, change the color depending on the where is our device? Yeah, let's change, for example, the color depending on the time, for example. How to do that? Well, we could either pass the time to the fragment shader and it would calculate it itself, or we could calculate it in the vertex shader and passing it to the fragment shader. Now, in this case, I would recommend calculate, like anything that you can calculate in the vertex shader, do it there instead of the fragments. Why? Because in this case, we only have 3 vertices, but for the pixels, or the fragment should I say, we have a lot of the, like a lot of pixels that the triangle would actually cover. So like the fragment shader would actually work once for every single fragment in the triangle, while this guy would only work on every single vertex. So would you rather do the calculation 3 times in our case, or would you rather do how much fragments or pixels we have in the triangle? So surely we should go to vertex as long as we can. So yeah, let's go with frag color equal color times time, for example, or let's say color is vic3. Okay, fine, let's say times vic3 sign of position, sign of pc dot time. Absolutely love this. Let's go. But yeah, there you go. And this should do the trick. So it would scale the color depending on the time. So yeah, there you go. But notice one thing here, is that the black color stays for a very long time. Why that is the case? And the thing is, because actually sine function goes from -1 to 1, and anything below 0 for a color would just get clamped, so you end up with 0, which is basically black. So basically, let me show you one cool website called Desmos. Okay, and a lot of my math I just learned, of course, other than high school math, most of it is usually because of shaders and because of, let's say, just, you know, graphing stuff in Desmos and just seeing how every variable changes the graph and stuff like that, and seeing every equation, what it does, whatever. Let me give you an example. For example, the sine function, it goes from -1 to 1, right? So let's say I want to, like, in terms of time, let's say plus t, and then we have this t slider, and notice what it does. Well, let's say minus t actually, and notice what it does. It actually just like offsets it moves the sine wave, or it offsets it, right? Look at that. I could even go ahead and go crazy and say t0, and they can make a point here, and I could actually change it however I want. This is pretty cool. And what happens when I actually do times some variable? I don't know, let's say s for scale or something. And this is what happens for that. And we could also say here, let's say 0 times s or something like that. Maybe let's make this cosine or something. Let's actually say t here. There you go. And there you go. Weird stuff, right? This is pretty cool. We could even animate this t. So this is actually what happens when I pass time as an offset to the cosine or the sine. As you can see, it just moves. But yeah, you got the point, right? Now, our problem here that I wanted to show you is that cosine or sine both actually gives you a value from -1 to 1. But the thing is, color goes from 0 to 1. So how we could map this output of the sine function to 0 to 1? Well, first of all, the size of this sine wave is 2 units, because it goes from -1 to 1, right? So 2 units. First of all, we need to actually make it 1 unit. So it goes, so the size is 1. So what I'm gonna do, I'm just gonna divide by 2 or multiply by 0.5. Now my sine wave is exactly 1 unit. Right now it goes from minus 0.5 to 0.5. Now this is good, but it's still going from like in the negative. I don't want it to do that. I want it to go from 0 to 1 instead of from minus 0.5 to 0.5. So I could just add this 0.5 so I could offset it. And there you go. So now the sine wave goes from 0 to 1. Let's go. And yeah, by the way, also you could do times x times something. Let's say this is basically the frequency. And then you like this basically changes how frequent is the change. And that's why it's called frequency. Otherwise, you could also look into it as the times 1 divided by t, which is like the period, or like divide by t instead, right? By t, which is like the period. And now, what happened there? So the period is basically right now, instead of actually controlling the frequency, right now you're controlling the period of the distance kind of between the waves and stuff like that. But anyways, whatever. This is just a little math explanation. Anyways, so right now what I gotta do basically times 0.5 plus 0.5 essentially, and there you go. Let's go. Let's see, and there you go. And notice right now it goes from 0 black to that color. And let's go. Pretty much. Notice that the color change is pretty slow, so we could change the frequency. So let's change the frequency now. Let's say pc.time times, let's scale it by, let's say 10. Let's just say 5, I guess. That's enough maybe. Or you could say times 0.1 to slow down the color change, the frequency basically. So let's see right now. And notice that it's pretty fast now. Faster. But yeah. There you go. There you go. That was a lot of cool stuff. So what I'd like to do now, I think how much time we have done, right? Yeah, I'm gonna stop the live stream at this point. So thank you for tuning in and see you later. Goodbye, everyone.